Hello and welcome to Apologetics 101. I'm your host, Brian, your resident Christian apologist, and today we are doing another GTF model video. Why am I doing so many of these videos? It's just so that I can promote this a lot more on my channel. I also want to defend aspects of the model to critics when critics try to attack it or come up with some new revolutionary idea that nobody else has come up with and deal with that. It doesn't happen very often, but it does happen. Sometimes I'm dealing with the same criticisms and that sort of thing. Today, though, we're going to be doing something different. Today we are going to be doing a big evidence video. I promised this video like early I promised it last year that I was going to do it early this year. And this video essentially is intended to reinforce the evidential foundations of my model. Now, just to be clear, I actually presented evidence in my very first video, the depth of the heat problem. I presented evidence there for my model. Um, some critics have tried to accuse me of not presenting evidence when I did present evidence. Obviously, in this video, I will be expanding on those, giving you more evidences and doing a lot more stuff. I'll be expanding on everything that I didn't, because I kind of streamlined the evidence. I gave evidence, but I streamlined it in my first video. So this is basically going to be reinforcing the evidential foundation. It's going to give more sources. It's going to give more evidence, more examples, and expand on those examples. And also it's going to be giving up a good deal of math as well. My model isn't math dependent, meaning that the validity of the mechanics of the model isn't dependent upon the math or the numbers. The numbers always follow the validity of my model. But to show that my model works, I do have math in my model to show that it does actually work. There are equations. Now, unfortunately, unfortunately, critics, and this is so nerve-wracking. Uh, I could present evidence, and then critics could put their blinders on and treat it like and pretend like I didn't present any evidence when I did. Um, or present or say that I treat it like I don't ever quantify anything. I've actually heard them say that in the comment section. Oh, he quantifies nothing. I quantify everything. Everything in my model, I've quantified right from the beginning. Depth of the heat problem. I got an entire video called Mathematical Defense. I did math also in my third video. I'm now doing it in my fifth video. You're going to see some in my sixth video as well. That's going to be coming out at the exact same time as this one. So yeah, I quantify everything. So that's just completely bogus claim. And there's a lot of criticism that's been going around on my model. So I will be defending that mostly in my next video. This one I wanted to focus mostly on the evidence. I will deal with some of the criticisms, but most of this is going to be focused in my next video, which is going to be called a critical defense. Um, but this one right here is going to be defending the evidential foundations of my model. And so without further ado, let's dive into the geothermal feedback model and evidential defense. All right, you notice the series intro is a little different. I'm actually taking this series. This was not intended to be a series, actually. It was never meant to be a series. It was part of the Genesis series because I had the depth of the heat problem video as part of the Genesis series. But I might be ending the Genesis series within the next few years. So I'm going to be taking this series out of the Genesis series and its own thing, and I'm gonna have to fix that in the Genesis series. The depth of the heat problem will still be part of the Genesis series, but and it will still be the first video in the playlist. If I think I have a playlist for the GTL model. If I don't, I will get a playlist. But it will be the first video on the playlist, still the depth of the heat problem, and I still consider it the first video of this unintentional series that I had formulated without thinking. But I'll, just in case if I put any more videos in it, I don't want because it's gonna be kind of open-ended. So I just kind of don't want to, if I end up closing the Genesis series off, I don't want to tie this to the Genesis series specifically. So I'm gonna just kind of do its own thing, separate from the Genesis series. So hopefully that is okay. And so let's dive in. All right. I'm going to be presenting a presentation. I have come up with like over 300 slides. So, so bear with me. All right. Um, so essentially, this is the geothermal feedback model and evidential defense. I just used the same screen I've been using. I will be doing a different one for critical defense. But because the critical defense is essentially one section that would have been part of this video, but I decided it would be better off as its own video, and so I have that as a separate video. But this one is geothermal feedback model and evidential defense is what my slide presentation is also called. All right, let's summarize the geothermal feedback model or GTF model. That is my personal model in response to the so-called heat problem that critics level against the Genesis flood. Okay, the geothermal feedback model, also known as the GTF model, proposes that the extreme geothermal activity associated with the global flood operated as a thermally driven positive feedback system rather than a one-dimensional heat catastrophe. In this framework, the Earth during the flood fractured as a coupled thermodynamic system in which geothermal heat production, high-speed mantle convection, high-speed advection, volcanic activity, of all which interacted dynamically in thermally driven positive feedback loop system. Instead of allowing heat to accumulate uncontrollably, the system responded to increasing heat by strengthening the very mechanisms that remove the heat from the planet. It also includes a number of cooling mechanisms, by the way, as well. Um, which I'll go into in a second. The model begins with the observation that the catastrophic tectonic activity would generate enormous geothermal energy through processes such as high-speed mantle convection. Well, actually, that's kind of poorly worded there. It's not that the mantle convection itself is generating energy, it's the fact that energy is generated from accelerated nuclear decay and other heat sources. So that's just to make sure that that's clear. And this actually speeds up mantle convection, and this triggers high-speed advection in the crust. Okay, um, and and from that, we also have global volcanism, and coupled with a number of cooling mechanisms like volcanic cooling, latent heat removal, cloud covering, that sort of thing. And of course, the heat releasing to space from the atmosphere. Um, However, the majority of this energy does not enter the oceans or atmosphere directly. The mantle acts as the primary thermal reservoir, possessing an enormous heat capacity given by C mantle equals mCp, which allows large quantities of energy to be absorbed with relatively modest temperature change. Heated crustal material is transported downward through high-speed advection into the upper mantle, preventing the bulk of geothermal heat from reaching the surface environment. At the same time, the fraction of heat that does reach the surface triggers several powerful cooling mechanisms, increasing ocean temperatures, accelerate evaporation, which transfers energy into the atmosphere through latent heat removal, intensified atmospheric circulation, evaporation, and storm systems generate extensive increased cloud covering, increased planetary albedo, and reducing absorbed solar radiation. According to P solar equals 1 minus alpha um, SA over 4. Elevated atmospheric temperatures also increase the rate of infrared radiation to space, governed by Stefan-Boltzmann relation. P equals sigma times A times T to the fourth power, allowing the planet to shed heat more effectively. Because these cooling mechanisms strengthen as temperature rises, hence the positive feedback loop, the flood climate behaves as a self-regulating thermal system. When geothermal heat production increases, convection advection increases, evaporation and latent heat removal increases cloud formation and rate of heat loss, all intensify, accelerating energy removal from the system. Conversely, if geothermal heat production decreases, those same mechanisms weaken, reducing heat loss and preventing excess cooling. This feedback behavior prevents the climate from diverging toward either catastrophic overheating or runaway freezing. The GTF model therefore resolves both major thermodynamic criticisms commonly raised against the flood geology. It addresses the traditional heat problem, quote unquote, by demonstrating how geothermal energy can be absorbed, redistributed, and removed, which you could also say regulated as well, through a network of feedback processes. At the same time, it resolves the so-called freezing problem, the inverse argument that reduces solar radiation during the flood would cause global temperatures to collapse. Also, it's more nuanced than that. Whatever causes the energy to be dealt with during the flood is sometimes argued that would be so drastic that it would freeze the planet. And my model actually deals with both objections actually. We'll talk more about that later. Directly to the thermal state of the system, the flood environment naturally stabilizes between these two extremes. In this way, the geothermal feedback model presents a coherent thermodynamic framework in which catastrophic geologic processes and atmospheric dynamics operate together to regulate planetary temperatures during the flood year. Evidence for the model feedback loops. Let's do some real quick defining of terms. My last video, I did do a terminological defense, so I went through a lot of these terms. So if you want to go back on that, you can go back over that. I also went over these terms in my depth of the heat problem video as well. So I talked about it then as well, but I just want to just kind of cover some of the basics. Feedback loops, a system that feeds back into itself. Negative feedback loop, a system that feeds back into itself by subtracting from the system, but then regulate that system back to homeostasis by redistributing back into the system. Positive feedback loops, a system that feeds back into itself to cause further increase to the system each time the system feeds back into itself. So in other words, everything increases with the system feeding back into itself. Examples of negative feedback loops, the water cycle, digestion, etc. Examples of positive feedback loops, ethylene released in fruits to cause further ripening, fever-induced sweating that causes reduction in body heat each time the heat increases, seismic activity and earthquakes, etc. I'm not going to go too far into these because I have covered these ad nauseum on other videos, so I'm not going to be trying to dive too deep into these terms because I've already dealt with them previously. Okay, initial perturbation. This I want to give you certain criteria that is necessary for a positive feedback loop. All right, an initial perturbation that displaces the system from equilibrium and produces a measurable response in at least one state variable, e.g., temperature, pressure, stress, velocity, melt fraction. Simplified, something has to kick the system out to a balance to start with. If nothing changes, nothing feeds back. This kick can be a temperature spike, pressure change, stress increase, or any disturbance like large enough to cause a real measurable response. It also needs to have a causal pathway back to the driver, a causal pathway linking the response back to the original driver, such the system's output feeds into its own input rather than acting solely as a passive consequence. Simplified, the system's response must loop back and affect the original cause. If the response just happens to and stops there, it is not a feedback. Feedback means the output must be part of the input. All right. The third one is positive loop gain. Loop gain means the magnitude of the feedback response increases the original perturbation rather than opposing it, at least over some operational range of system states. Simplified, the response has to make the original change stronger, not weaker. Even if this only happens over a limited range, the system must amplify the disturbance rather than counteract it. Okay, not four, non-linear system behavior. Non-linear system behavior where changes in state variables, temperature, stress, velocity, permeability, alter governing parameters themselves, preventing simple linear damping from dominating. Simplified, as the system changes, its rules change too. For example, hotter material flowing more easily or stressed, rocks breaking faster. This prevents the system from simply settling back to normal in a smooth, predictable way. Number five, state-dependent coupling. State-dependent coupling in which the strength of interactions between system components increase as the perturbation grows, e.g. temperature dependence, viscosity, pressure dependence, melt generation, stress dependence, permeability. Uh, Simplified, the more the system changes, the more tightly its parts interact. In other words, changes makes more change easier. The system becomes increasingly um, sensitive as it as it moves away from equilibrium. Temporal coherence. Temporal coherence that such that the feedback operates on timescales comparable to or shorter than stabilizing processes, allowing amplification to occur before equilibrium is restored. Simplify. The feedback must act fast enough. It stabilizes forces have time to cancel the change before feedback strengthens it. The loop never takes off. Timing matters as much as strength. 7. Energy or mass transfer pathways. Energy or mass transfer pathways that allows internal energy to propagate through the system rather than remaining localized, e.g. advection, convection, fluid flow, mechanical deformation. Simplified, there must be a way for the effect to spread through the system. Heat, material, stress, or motion has to move from where it starts to where it can reinforce the process. Threshold or bifurcation behavior. Threshold or bifurcation behavior where crossing critical value stress, temperature, pressure causes the system to transition to a new dynamic regime with stronger feedback coupling. Simplified, many systems have normally until a behave normally until a critical point is crossed. Once that threshold is passed, the system suddenly behaves very differently, often allowing the feedback to become much stronger. Okay, you see what I'm doing here? I'm giving you the criteria necessary for why something would be a positive feedback loop, and this is necessary in order to show you that the kinds of the volcanic eruption shows these kinds of positive feedback loops, and all I did was just scale it to the intensity of blood. I will also show you why the give you the flood matches these criteria in determining that it is a positive feedback loop. Number 9, partial decoupling from external damping. Partial decoupling from external damping, meaning that the stabilizing mechanisms exist but do not dominate the system response within the operational regime of the feedback loop. Simplified, stabilizing forces don't disappear, but they don't fully control the system anymore. Feedback dominates for a time, even though opposing forces still exist. 10. Finite but non-zero saturation limits. Finite but non-zero saturation limits where feedback amplification is constrained by physical bounds rather than halted immediately by restoring forces. Simplified, the feedback doesn't grow forever, but it doesn't stop immediately. It is limited by physical boundaries, not by instant stabilization. 11. Feedback persistence over a defined interval. Feedback persistence over a defined interval such that application is sustained long enough to measurable altered system behavior or trajectory. Simplified, the loop must last long enough to matter. A momentary amplification that ends instantly is not a meaningful feedback loop in physical systems. System openness. System openness allowing exchange of energy or mass with surrounding reservoirs, which permits continued feedback operation rather than rapid internal exhaustion. Simplified, the system must be able to exchange energy or material with its surroundings. Completely closed systems usually self-cancel too quickly to sustain feedback. 13. Directional reinforcement. Directional reinforcement, where feedback effects constantly act in the same direction as the initiating perturbation rather than oscillating randomly. Simplified, the feedback constantly pushes the system in the same direction as the initial change. Random or altering processes or responses don't qualify as positive feedback. 14. Self-reinforcing parameter evolution. Self-reinforcing parameter evolution in which the system's evolving state makes future feedback more effective than earlier stages. Simplified, as the system evolves, it becomes better at feeding back. The conditions that allow feedback improve as the feedback operates. Evidence for positive feedback loops. Does the flood's conditions meet these conditions? All right, essentially what I'm doing here is I am going to be, I already gave the conditions that are necessary for a positive feedback loop. I went through, I believe, 13, 14 criteria. And so now I am going to be going through those criteria again, except this time I am going to be looking at the condition of floods to see if they meet these conditions for a positive feedback loop. Initial perturbation. Genesis presents the flood's onset as an abrupt global scale disturbance. All fountains of the great deep burst forth, and the windows of the heavens were opened. Genesis 7:11, circumference 8:2. Whatever one takes fountains of the great deep to mean physically, the text itself depicts a sudden initiation event that would plausibly correspond in flood model terms to rapid lithospheric rupture, massive fluid release, and sharp changes in pressure, stress, and heat flow. Exactly the kind of kick, quote unquote, kick, that moves a coupled geosystem far from steady state. Accelerated nuclear decay and other deep heat sources provide a rapid system-wide thermal perturbation, abruptly displacing the mantle lithosphere system from equilibrium by increasing temperature, pressure gradients, and internal energy density. Okay, causal pathway. Number 2 causal pathway, back to the driver. A feedback loop requires a closed causal chain. The system's response must feed back into the initiating driver. In many non-GTF flood models, e.g. CPT-style catastrophic plate motion scenarios, once large scaled rupture and rapid plate motion began, that motion itself increases deformation, faulting, and slab descent, which promotes further mantle flow and more tectonic recognition, i.e. the response accelerates tectonics, reinforces the original driver, mechanical stability, and rapid lithospheric dynamics. In fact, the actual runaway subduction, as proposed by Dr. John Baumgartner, is actually a positive feedback loop. It's actually a runaway. It actually is a positive feedback loop. It has a runaway effect to it, but it is a positive feedback loop. The biblical description of the fountains, quote unquote fountains, continuing Genesis 7:11 and 8:2, is consistent with this sustained causal sequence rather than a single isolated pulse. Increased internal heating lowers viscosity and promotes deformation, which feeds back into further mantle flow, tectonic motion, and melt generation, directly linking the system response back to the initiating disturbance. Positive loop gain. In flood model terms, positive loop gain is satisfied if increasing in tectonic slash magmatic activity produce conditions that increase tectonic magmatic activity further over at least a range. For example, further subduction leads to more slab pull, rollback, mantle circulations leads to more melt generation, um, uh, volcanism leads to more weakening, and mechanical failure leads to faster plate motion. The flood narrative emphasizes persistence and intensification over time. Water prevailed, quote unquote, prevailed and rose, Genesis 7:17 through 20, which is at least compatible with an episode where the dominant heat internal dynamics amplify rather than damp immediately. The conditions of the flood, in other words, is gaining momentum with time. Rising temperatures increase convection velocity and melt production, which further weaken the lithosphere and enhance magma transport, producing amplification rather than damping over the active regime. Okay, number 4, nonlinear system behavior. Geophysical systems are nonlinear because viscosity yields strength, permeability, melt fraction, and frictional behavior change sharply with the temperature, pressure, and stress. Flood scale conditions described in the text. Global upheaval, rupture, burst forth, and sustained extreme rainfall slash runoff. Genesis 7:11 through 12 imply regime shifts where ordinary linear small perturbation assumptions would not hold. In CPT type framework, once the lithosphere enters a runaway failure mode, the governing parameters, effective viscosity, strength, coupling, friction, can change rapidly, a hallmark requirement for positive feedback. Temperature dependent viscosity, stress dependent failure, and permeability dependent flow ensures that heating from and which is a abbreviation for accelerated nuclear decay, and volcanism drives non-linear changes in system behavior rather than linear relaxation. Number 5, state-dependent coupling. Flood models commonly posited that as deformation increases, coupling between processes strengthens. Fracture network increased permeability. Permeability increases fluid flow. Fluid flow weakens rock and promotes further fracture melting. And magma transport reduce effective strength. Reduced strength increases deformation rates. The text fountains language, Genesis 7:11, 8:2, strongly suggests sustained pathways for deep sourced fluid slash energy to communicate upwards, which is exactly the kind of state dependent coupling. More rupture leads to more flow, and more rupture needed for an amplified loop. As heating, deformation, and volcanism intensifies, coupling between mantle and flow, subduction and magma ascent strengthens, making further increases in activity easier as the system evolves. Number 6, temporal coherence. A positive feedback must operate on timescales fast enough to outrun stabilizing processes. The flood timeline is explicitly short. Onset, Genesis 7:11, intense phase, 40 days of rain. That's torrential rain. Sometimes critics get that mixed up and they think that they only rain 40 days. It actually rained throughout the flood. That is the initial raining in the beginning of the flood. Genesis 7:12, uh, and I actually proved this because the fountains of the great deep wasn't actually closed until day 350, um, and as well as the windows of heaven. Waters prevail, and it also actually says the water rose too, so it wouldn't do that without raining. Waters prevailing, Genesis 7:24, and later turning point when God caused a wind to blow and the fountains were closed, Genesis 8:1 through 2. Many flood models argue that the dominant technomagnetic processes must be rapid, catastrophic, rather than gradual, precisely because the event is time compressed. That time compression is the very condition that allows amplification to manifest before slow conductive equilibration can dominate. Increased convection speeds allow feedback process to operate faster than conductive cooling or mechanical relaxation, preserving amplification on flood timescales. Number 7, energy or mass transfer pathways. Flood conditions explicitly involve mass transport, water, and sediments, and by common flood model inference, intense internal transport as well. Manta flow, magma ascent, slab motion. Fountains of the Great Deep, Genesis 7:11 applies an internal to surface pathway. Widespread volcanism and hydrothermal circulation are standard elements in many flood reconstructions, even outside my own model. These pathways, advection, convection, fluid flow, are exactly what let local perturbations propagate system-wide rather than remain confined. Enhanced magma ascent, slab descent, hydrothermal circulation, and volatile transport provide efficient pathways for heat and mass to propagate through the system rather than remaining localized. Number 8, threshold or bifurcation behavior. The narrative itself reads like a threshold event. Normal world leads to sudden rupture and global inundation, Genesis 7:11. In geosystems, thresholds are common. Once stress exceeds strength, failure cascades. Once melt a fracture or probability crosses a critical value, transport accelerates. Once subduction speed exceeds a regime boundary, coupling changes. Flood models typically treat the onset as a quote unquote tipping into a different dynamic regime, catastrophic tectonics hydrology, which is the bifurcation criterion in plain form. Once thermal and mechanical thresholds are exceeded, rapid melting, lithospheric rupture, and runaway tectonic motion transition the system into a new dynamic regime with stronger feedback coupling. Number 9, partial decoupling from external damping. Damping exists, radiation to space, conductive smoothing, viscosity, viscous dissipation, but the criterion is that damping does not immediately dominate during the amplifying interval. The flood account explicitly separates phases, initiation and prevailing, Genesis 7:11 through 24, versus cessation, abatement, fountains closed, Genesis 8:2, mentioned that earlier, water recede, also mentioned Genesis 8:3 through 5. That structure supports the idea that whatever stabilizing processes normally quote unquote win were temporarily overwhelmed, then reasserted. Later reasserted. This is exactly what partial decoupling means in feedback language. Although cooling mechanisms exist, accelerated heat input and rapid transport prevents damping from dominating during the active phase, allowing feedback to control system behavior temporarily. Number 10, finite but non-zero saturation limit. Positive feedback cannot grow without bound. It saturates when constraints bite, available buoyancy, geometry, material limits, depletion of driving gradients, Closure of pathways. The flood story includes explicit shut-off, quote-unquote shut-off language. Fountains were closed, Genesis 8:2, and abounded duration of maximal conditions. Waters do not rise indefinitely. Genesis 17 through 20. Later they recede. Genesis 8:3. In feedback terms, that's consistent with saturation and termination by constraints rather than an endless runaway. Volcanism, convective vigor, and tectonic motion are physically bounded by material limits and geometry, ensuring amplification saturates rather than diverges indefinitely. Number 11, feedback persists over defined interval. The flood is described as sustained over months with waters prevailing 150 days, Genesis 7:24, before a turning point, Genesis 8:1 through 3. That is long enough within the flood framework for amplified coupling processes, tectonics, volcanism, sediment transport, hydrothermal circulation, to have major system level effects. The criterion is not for quote unquote forever, but quote long enough to measure alter trajectory end quote. And the narrative's multi-month dominance satisfied that at the level of event structure. Sustained heat generation and rapid transport maintain feedback actively long enough to produce global scale geological effects rather than transient disturbances. Number 12, system openness. A system that exchanges energy and mass with surrounding reservoirs can sustain dynamics longer than a closed one. Flood conditions are explicitly open, enormous atmospheric slash oceanic exchange, windows of the heavens, Genesis 7:11 through 12, global hydraulic cycling, Genesis 8:1 through 2, and massive erosion slash deposition implied by the waters prevailed in later recession, Genesis 7:17 through 24, 8:3 through 5. In flood modeling terms, openness also includes internal-external exchange through deep source fluid slash heat via fountains, enabling continued operation of a couple processes rather than immediate internal exhaustion. Exchange of energy and mass between mantle and crust, hydrosphere, sphere, and atmosphere allows continued feedback operation without rapid internal exhaustion. All right, there are three types of systems. Okay. Open system, closed system, isolated system. Open system is mass and energy can enter and exit. Closed system is mass cannot enter or leave, but energy can enter and exit the system. Isolated system is completely isolated. Mass and energy cannot enter or exit the system. Some people confuse closed system with isolated system. These are not the same thing. In a closed system, mass can actually come and go or excuse me, backwards. Energy can come and go. That's a common misconception where they just assume that a closed system energy can't come and go. I've heard one critic try to say that no closed system is perfectly closed, but I think it's because he's confusing closed system with isolated system. No closed system would, by definition, a closed system would not allow energy to come and go, regardless, or would allow energy to come and go. It's matter or a mass that cannot come and go in and out of a closed system. But energy can actually come and go in and out of a closed system. Open system, mass and energy can come and go. Where a closed system, only energy can come and go, mass cannot. Isolated system is completely isolated. Mass and energy cannot enter or exit the system. Okay. The Earth is an open system. Mass and energy can both exit and enter the system of the planet. Not, astronomers or astronauts could not leave the planet. We couldn't send shuttles up. We couldn't send we wouldn't be able to send satellites up. We wouldn't be able to get signals back. We wouldn't be able to, energy could not come and go. So Earth is a completely open system. Now, a lot of critics will treat the Earth like it's a isolated system. They'll claim that they don't believe it's an isolated system, and they don't, and they probably don't. that believe it's an isolated system. I don't think they believe it. A lot of them will say they don't believe it. Now, I have ran into critics that actually believe that the Earth was a closed system. So they didn't just treat it like it was. They believed it was. But there is a critic I know on my channel that gets all mad when I talk about this because he thinks that I'm accusing him, like misrepresenting him. Yes, I understand that he knows that the Earth is an open system, but when he goes and talks about Stephen Boltzmann's law, or when I'm sitting there trying to discuss my model with him, he treats the Earth like it's a closed system, like it, and that is implied in his arguments. He might not believe that. He might not cognitively recognize that. He might believe strongly that the Earth is an open system. That's fine, but that's not the way he argues. So, and the way he argues is different than what he actually believes himself. So that's the issue. Um, all right. The Earth is an open system. Mass and energy can both exit and enter the system of the planet. A system, according to science, pertains to an independent or interrelated series of objects comprised and functioning as a whole. Essentially, just about pretty much anything in science is considered a system. Even the universe is considered a system, because it has interrelated parts to it. So, the only thing that cannot interact with each other, if assuming that other universes exist, is other universes, obviously. But everything else in our universe is a system in some way or another. Whether we're talking about ecosystems, whether we're talking about biological systems, whether we're talking about the Earth. Earth is a system. So just about everything in science is pretty much a system. All right, the Earth itself is a system. All right. Let's talk about directional reinforcement. 13. For positive feedback, the responses must consistently push in the same direction as the initiating perturbation during the amplifying phase, not merely oscillate randomly. The flood narrative emphasizes monotonic escalation early. Waters rise and prevail, Genesis 7:17 through 20 to 24, translating into that system dynamics, the processes driving inundation, mechanical failure, and global transport are portrayed as continuing in a reinforcing direction until a later explicit reversal. Genesis 8:1 through 3. That rise then turn, quote unquote, rise then turn pattern is what directional reinforcement plus later shutoffs look like. During the early and middle flood phases, the system evolves in a consistent direction, increasing inundation, deformation, and transport. Only later does a reversal occur, which is normal for feedback-driven events once constraints assert themselves. Increasing heat, deformation, and transport reinforce the same direction trend, greater activity until constraints or shut-off mechanisms assert themselves. In other words, once the triggers are no longer triggering the event, the feedback loop will end ultimately. So it's all have one directional. So it's not like it has to go on forever. Even a runaway positive feedback loop, like a runaway greenhouse effect is a positive feedback loop. A runaway greenhouse effect is a positive feedback loop with a runaway effect. And even that actually has an end. Once the greenhouse gases are filtered out, and eventually the runaway greenhouse effect will end. So all positive feedback loops have a end to them. Number 14, self-reinforcing parameter evolution. This criterion is met if the event changes the system in ways that make continued amplification easier. Fracture networks expand permeability, increases weak zones, localized deformation, thermomechanical gradients steepen, and transport pathways widen. The biblical description implies a progressive global scale disruption, Genesis 7:11 through 20, followed by later closure/abatement, Genesis 8:2 through 5, which is consistent with a period in which the system state quote unquote state evolves toward greater connectivity and efficiency of transport, more conduits, less strength, more mobility, until constraints or shut-off mechanisms in the phase. Progressive weakening increases permeability, faster flow, and expanded transport pathways make continued feedback more effective as the event unfolds. Does the flood conditions meet these positive feedback loop conditions? Yes, it does. The flood conditions meet all 14 criteria for a positive feedback loop, from heat generation to how the system interacts and responds to itself and geological and thermal triggers. It is clearly the best conditions to trigger a positive feedback loops within the volcanic activity, seismic activity, intense and extreme internal pressure, as well as fracturing of the crust, intense heat sources generating a lot of heat, runaway subduction, fountains of the Great Deep, high-speed convection, and advective processes, volcanic activity on a global scale, etc. The positive feedback loop mechanically dependent would have been driven by the very heat that had been generated, including stellar nuclear decay, fountains of the Great Deep, runaway subduction, frictional heat, meteor impact events, and volcanic heat. This heat would have heated up the mantle, accelerating mantle convection and triggering high-speed advection in the crust, removing the heated material in the crust at an accelerated rate. Okay, I got some sources here for that on the positive feedback loops. As the surface warms up, part of the ice or snow covered area melts, reducing the surface albedo alpha, increasing solar flux absorbed by the surface, absorbed solar radiation, and surface temperature variations, thus reinforcing each other via a positive feedback loop. And it gives you the sources there. Eruptive style depends on a set of feedback involving interrelated magma properties and processes. For most of these are magma viscosity, gas loss, and external properties such as conduit geometry. Ultimately, these parameter controls the speed at which magma ascends, decompresses, and outgas en route to the surface, and thus determine eruptive style evolution. End quote. Layer viscosity, temperature dependent viscosity, and surface plates have an important effect on scale and morphology of the structure. In spherical model of mantle convection, we find that long wavelength structures can be produced either by layered viscosity with a weak upper mantle or temperature dependent viscosity, even in the absence of surface plates, corroborating earlier studies. However, combining the layer viscosity structure with a temperature dependent viscosity results in structure with significant shorter wavelengths. Our models show that the scale of convection is mainly controlled by the surface plates. Supporting the previous two-dimensional studies, our models with surface plates layered and temperature dependent viscosity and internal heat explain mantle structure inferred from seismic topology. The models show that hot upwellings initiate the core mantle boundary CMB. This is, by the way, from peer review with linear structures, and as they depart from CMB stands for core mantle boundary, the linear upwellings quickly change into quasi-cylindrical plumes that dynamically interact with the ambient mantle and surface plates while ascending through the mantle. A linear upwelling structure is generated again at shallow depths, greater than 200 kilometers, in the vicinity of diverging plates. Margins become the surface plates at shallow depths. Cold downwelling sheets form at converging plate margins. The evolution of downwelling sheets depends on the mantle rheology. I'll explain rheology in the next video because that's going to be important in responding to a particular critic. The temperature-dependent viscosity strengthens the downwelling sheets so that the sheet structure can be maintained throughout the mantle. The tendency for linear upwelling and downwelling structures to break into plume-like structures is stronger at higher Rayleigh numbers. Our models also show the downwellings to break into plume-like structures is stronger at higher Rayleigh numbers. Our models also show that downwelling to first order control surface, plate motions, and the locations and horizontal motion of upwellings. Upwellings tend to form at stagnation points, predicted solely from the buoyancy forces or of downwellings. Temperature dependent viscosity greatly enhances TB, sending the velocity of developing upwelling plumes, and this may reduce the influence of global mantle flow on the motion of plates or plumes. Excuse me. Our results can explain the anti-correlation between hotspots distribution and fast seismic wave speed anomalies in the lower mantle, and may also have significant implications to the observed stationarity of hotspots. And there's a source there too if you need to see that. The response of the various, I got like several sources here for that. The response of the various climatic processes to climate change can amplify positive feedback. This parentheses is theirs. It's in the original source. But positive feedback or damp negative feedback, the initial temperature perturbation. An example of a positive feedback is the surface albedo feedback. When the surface temperature rises, part of the ice and snow melts, leading to an increase in the solar radiation absorbed by the surface and to an enhanced surface warming. Positive feedbacks can lead to instability on Venus. For example, a positive feedback is thought to have evolved into a runaway greenhouse effect. However, positive feedbacks can exist in stable systems. This paper presents a simple representation of a positive feedback in both a stable and an unstable system. I actually had a older creationist that thought that all positive feedback loops lead to runaway effects. That's not true. It can lead to a runaway effect, but it doesn't have to. And of course, even the runaway effect actually has a end to it. So I wouldn't mind if that was the case, but Rolando doesn't even lead to a runaway effect anyhow, and it wouldn't matter if it did. But 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 in the case, it doesn't lead to a runaway effect. But not all positive feedback loops lead to a runaway effect. As the paper says, that is absolutely 100% true. This paper presents a simple representation of a positive feedback in both stable and unstable system. A simple experimental device based on a scale principle is introduced to illustrate the feedback loop and its stabilization or runaway regimes. Stabilization can achieve whether the amplitude of the positive feedback declines, e.g., saturation of the feedback, or remains constant. The device can also be used to illustrate the existence of tipping points, which are threshold values beyond amplification due to feedbacks or the stability of the system suddenly changes. The physical equations of the device are established in the framework of the feedback analysis. Key features to understanding why positive feedback does not necessarily lead to a runaway effect are described. And that gives you the source right there. All right, I just think this might be my last one on this. The broadest definition of a feedback is a process that, when included in the system, makes the forcing a function of the response. In other words, some function of the output is fed back into the input. The curve of equation 8, some of the equation in that particular paper, is shown in figure 3 for a minus proportionate or proportionate to greater than L greater than 0, G greater than 1, and I put sick because that's how it's in the paper. Thus, the inclusion of the feedback has damped system response, i.e. T is greater than TO, and it is therefore termed a negative feedback. For 0 is greater than, or excuse me, less than, that's T is less than TO, and it is therefore termed a negative feedback. For 0 is less than ELF, less than 1, G is greater than 1. Thus, the inclusion of a feedback has amplified the system response and is therefore termed a positive feedback. The 1 over 1 minus ELF behavior of the gain is extremely important and has critical implications for dynamical systems. For instance, there is a high degree of asymmetry asymmetry between positive and negative feedbacks, which is simple and direct consequence of equation 4. Again, talking about equation in the model in the paper. For ELF, is greater than or equal to 1. 6 is undefined in settling of equations 2. Da, da, da. It was implicitly assumed they knew a equilibrium was possible, but this is not necessarily so, as the fraction of the output fed back into the input exceeds 1 lambda 0. The basic equilibrating tendency of the reference system can no longer keep up with the implication from the feedback process, and catastrophic runaway growth ensues. In real systems, this cannot continue indefinitely. Eventually, some other physical processes must arise to produce a new equilibrium. The model system represents by equations some other physical process must arise to produce a new equilibrium. The model system represented by equation 2 has broken down because of that other physical processes has been included. Note also that the not uncommon misconception that a positive feedback loop or positive feedback automatically implies a runaway feedback is not true. So if the oldest creationists you suggested that, here's that. You heard it. Okay, we're going to be talking about evidence of positive feedback loops associated with volcanic eruptions. And we're going to start with the 1783 to 1784 Lakey Fissure eruption, Iceland. I did a streamlined version of this in the Death of the Heat problem video, where I went through several lines of evidence that these kinds of positive feedback loops are indeed indicative of volcanic eruptions that occurred. So we have examples in the present. I just simply scaled this to that of the global flood. And so this presented evidence for my model. But uh, I wanted to go much more in depth, in much more detail, expand it out, maybe give more examples, things like that in this particular evidence video. All right, the first one we're going to start with is Lake Fissure eruption, Iceland. All right. This is one of the strongest examples of these types of dynamic positive feedback loops. Lakey is not just a quote unquote big eruption per se. However, it is one of the clearest real world examples of a volcanic system entering a positive feedback regime involving magma supply, pressure release, crustal failure, volatile release, atmospheric coupling, and climate response, all without requiring speculative physics. Event overview, baseline facts, location Iceland, Mid Atlantic Ridge, duration 8 months, June 1783 to February 1784. Style fissure eruption, 27 kilometers long, lava volume 14 to 15 kilometers cube, basalt, gas output, enormous SO2, fluorine, halogens, climate impact, hemisphere cooling, crop failures, mortality spike in Europe. Initial perturbation, remember the various conditions necessary for a positive feedback loop. Initial perturbation, the trigger, began with deep magma injection along an extensional tectonic setting. Once dikes propagated upward and breached the surface, pressure was released along a long fissure system rather than a single vent. This matters because pressure release increased melt ascent, not reduced it. Decompression increased volatile exsolution, which increased eruptive vigor. Eruption itself reduced overburden pressure, feeding back into the magma supply. This is the first hallmark of a positive feedback loop. The response, quote unquote, the response eruption enhances the cause magma ascent. 2. Pressure melt eruption feedback core loop. Once lava began erupting continuously. Lithostatic pressure dropped along the fissure. Decompression melting increased in the mantle source. Melt supply to the fissure increased, not decreased. New eruptive episodes followed earlier ones repeatedly. This is a classic pressure release feedback loop. More eruption leads to less pressure, leads to more melting, leads to more eruptions. This positive feedback loop it persisted for months, not just hours or days. It lasted for approximately 8 months. 3. Crustal weakening, permeability feedback as lava flooded the surface and dikes intruded the crust. Fracture networks expanded, permeability increased, magma transport pathways became more efficient over time. In feedback terms, transport efficiency improved as transport continued. That is self-reinforcing parameter. 4. Advective heat transport dominates conduction at Lakey scale eruption rates. Heat was transported by mass motion, lava plus gas, not conduction. This allowed enormous heat flux without catastrophic local melting of the crust. Heat removal scaled with eruption intensity. This mirrors one of the most important GTF ideas. Advective transport allows rapid heat relocation without local thermal runaway. Even though Lakey is far smaller than flood volcanism, the mode of transport is the same. 5. Atmospheric coupling, volcanic cooling feedback. Here is where Lakey becomes especially relevant to this heat problem framework. The eruption injected SO2 into the upper atmosphere, ash and aerosols over continental scales. This produced increased cloud condensation, nuclei, reduced incoming solar radiation, measurable surface cooling. So while internal heat release increased, surface temperatures decreased. Positive feedback in the geologic system coexisted with net cooling in the climate system. 6. Hydrologic and latent heat interaction often overlooked. Although Iceland is not globally flooded at this time, Lakey still involved lava ice interaction, lava groundwater interaction, steam generation, and latent heat removal. Phase changes absorb vast amounts of energy without raising temperature proportionally. This is a small scale analog to the GTF model's flood work or flood water latent heat removal mechanism. Lakey demonstrates that volcanic systems can transfer large amounts of thermal energy into phase changes, steam generation, melting, degassing. Limited temperature rise, the flood would vastly amplify this same mechanism through global water coverage. 7. Conceptual parallels to the GTF model. What Lakey shows empirically is that volcanic systems can enter sustained positive feedback regimes. These regimes can increase heat transport efficiency. They can coexist with strong cooling mechanisms. They can terminate naturally when constraints assert themselves. The GTF model scales these same physical principles, but at a global scale: regional versus global, months versus the flood year, local volcanism versus global volcanism. All right. More evidence of positive feedback loops with volcanic eruptions of Mount Tambora, 1815, Indonesia. All right. Tambora is arguably the clearest historical demonstration that massive volcanic heat release can coincide with net planetary cooling while still exhibiting positive feedback behavior during eruption escalation. Key reasons: it ranks second highest as a parallel, one of the largest explosive eruptions in recorded history. That's according to a volcanism dating base that actually has all these volcanic eruptions and volcanism and volcanic eruptions on them. Clear feedback escalation prior to climax, massive stratospheric aerosol injection, well-documented global cooling response explicitly shows that cooling mechanisms do not prevent eruption amplification. Event overview, baseline facts, location, Samoa, Indonesia, subduction zone arc, date April 1815, style Plinian to ultra Plinian, ejected volume 160 kilometers cube, dense rock equivalent, column height 40 plus kilometers, stratospheric injection, SO2 release tens of megatons. Uh, Climate effect: the year without a summer, 1816. This is a very famous eruption. It's been known to be called the year without a summer because of the volcanic cooling effect. The positive feedback loop during the eruption escalation: one, initial perturbation, magma chamber overpressure, tambor, began with prolonged magma accumulation, volatile rich magma, increased chamber overpressure, early explosions did not relieve pressure sufficiently, instead they fractured surrounding rock, increased permeability, allowed deeper, more volatile rich magma to ascend. This is the first feedback step. Partial eruption leads to conduit opening, which leads to increased magma flux. 2. Conduit permeability feedback: as eruptions intensify and increase, conduits widen, wall rock was thermally and mechanically weakened, gas escape became more efficient, ascent velocity increased. This is classic state dependent coupling. More eruption leads to easier eruption. Which leads to more eruptions. The system did not stabilize until the chamber catastrophically collapsed. 3. Volatile exsolution feedback. Tambora's magma was volatile rich. As magma ascended, pressure dropped. Volatiles exsolved explosively. Expansion, fragmented magma, fragmentation, increased surface area. Increased surface area, enhanced gas release. That's a continuing fragmentation feedback. Exsolution leads to fragmentation, which in turn leads to faster exsolution. Thermal, nonlinear, and runaway escalation. Tambora did not ramp up linearly. Instead, eruption intensified, jumped discontinuously. Plume height increased dramatically. Eruption transitioned to ultraplinian behavior. This is threshold bifurcation behavior, a key positive feedback criterion. Cooling mechanisms activated during maximal heat release. This is where Tambora becomes extremely relevant to the GTF model. 5. Stratospheric aerosol feedback. Tambora ejected sulfur gases directly into the stratosphere. SO2 leads to sulfate aerosols. Aerosols increased planetary albedo. Increased solar radiation was reduced. Result: global surface cooling of 0.5 to 1.0 degrees Celsius. Crop failures worldwide. Snow in June in parts of North America. 6. Energy partitioning, heat versus radiation. Most of Tambora's thermal energy did not remain in the crust, did not catastrophically overheat the surface, but was redistributed via fragmentation, gas expansion, atmospheric transport, radiative blocking. This illustrates a core GTF distinction. Energy can be effectively removed from the problem domain long before it finally radiates into outer space. Meaning it could be, from the like the areas, like it'd be really fast move from like the crust and stuff. Feedback termination by structural collapse. Tambora did not stop becoming cooling. One, it stopped because the magma chamber roof collapsed, pressure support was lost, the system mechanically shut down. This is a finite saturation, not damping dominance. Relevance to the GTF model: Tambora demonstrates three principles central to GTF logic. Heat release does not imply surface overheating. Tambora released extraordinary thermal energy yet caused global cooling. This directly undermines the claim that the heat problem necessarily causes thermal catastrophe. 2. Cooling scales with eruption intensity. The stronger the eruption, the higher the plume, the greater the aerosol spread, the stronger the cooling. This is a negative feedback nested inside a positive one, exactly the architecture that is described by my model. Although the system is on a positive feedback loop, it must imply a negative feedback loop with the flood waters being replenished by rain via the water cycle. 3. Termination occurs by constraint, not exhaustion. Tambora didn't run out of cooling, it hit a structural limit. The external trigger collapsed. The GTF model similarly distinguishes effective removal during the event from final removal via radiative removal to space afterwards. Conclusion: why Tambora matters for flood scale reasoning. If one volcano can enter a continuous eruptive feedback, inject aerosols globally, cool the planet while erupting, then global volcanism during the flood multiplies the mechanism, increases surface area, increases aerosol production, increases cloud albedo coupling, and increases latent heat pathways via water interaction. All right. The next one we're going to look at is Hawaiian hotspots. These are modern day examples of volcanic activity. All right, basic facts, tectonic setting, interplate, not a plate boundary, source, deep mantle, thermal anomaly, mantle plume, age, active for, this is the secular age, 80 to 100 million years according to the secular timeline. The flood timeline probably active since the global flood. Volcanic style, predominantly basaltic, effusive shield volcanism, magma temperature 1,200 to 1,300 degrees Celsius, hotter than the average MORB. That's actually an acronym. I'll get into that later. Crustal setting, thick, oceanic lithosphere, 90 to 100 kilometers beneath Big Island. Current expression, Kalua, Mana Loa, Lohi, Lohi, Seamont, whatever that means. Alright, the positive feedback loop in the Hawaiian hotspot, initial perturbation, anomalous hot mantle system begins with hotter than ambient mantle material rising beneath the Pacific plate. The temperature anomaly lowers mantle viscosity, increases buoyancy, promotes sustained upwelling. This is the seed condition for feedback. And temperature changes, alters flow behavior. 2. Temperature viscosity, flow feedback, core loop, mantle viscosity is strongly temperature dependent as plume material rises. Temperature remains elevated and viscosity decreases, flow velocity increases. That produces a reinforcing loop. Hotter mantle leads to lower viscosity, leads to faster upwelling, leads to sustained heat transport. This is true positive feedback, but it operates deep in the mantle, not at the surface. 3. Decompression, melting feedback as the plume ascends. Pressure drops, partial melting increases. Melt separates from solid mantle. Mantle extraction reduces density, increases buoyancy of remaining mantle, helps maintain plume ascent. So you can get upwelling leads to upwelling leads to compression melting, which leads to buoyancy enhancement, which leads to continued upwelling. This is pressure melt flow feedback, structurally similar to flood basalt promises, though far slower. 4. Lithospheric weakening and transport efficiency. Repeated intrusion beneath Hawaii. Thermally weakens the lithosphere, creates long-lived magma conduits, localizes volcanic activity that leads to easier magma ascent, which leads to sustained volcanism, which leads to further weakening. This is self-reinforcing parameter evolution, one of the key criteria for positive feedback. 5. Dominant cooling mechanisms at the surface. Hawaii volcanism is one of the best real-world demonstrations that massive heat flux can coexist with efficient cooling. Lava enters the ocean, which leads to rapid quenching. Ocean absorbs heat, which leads to convection plus latent heat. Um, uh, atmosphere sees minimum long-term warming, so heat transport is large, but temperature impact is capped. This distinction is central to the GTF model's effective versus final heat removal framework. Conclusion: the Hawaii hotspots effectively shows mantle dynamics in relation to positive feedback loops and thermal mechanisms which are relevant to the GTF model system, but obviously on a much smaller scale. The Hawaiian hotspot demonstrates the temperature-dependent mantle viscosity, the decompression, melting, and magma transport can form long-lived positive feedback loops, while efficient oceanic cooling prevents surface thermal runaway. All right. We're going to do some um, underwater volcanism here. Look at some underwater evidence for volcanic activity underwater. Because after all, some of the volcanic activity will be taking place underwater after all. So I decided to look at some volcanic eruptions that actually occurred underwater. The first one we're going to do is the mid-ocean ridge submarine volcanism. That's the first one we're going to do. Okay. Basic facts: global extent 75,000 kilometers long, interconnected volcanic system. Tectonic setting: divergent plate boundaries. Volcanic style: submarine basaltic, mostly effusive. Magma type: morb. Now this is what I was talking about earlier. The morb means mid-ocean basalt. Okay, that's what it means. It means mid-ocean basalt. Water depth typically 2 to 4 kilometers below sea level. Heat output dominant source of Earth's internal heat loss today. Cooling environment, continuous contact with cold ocean water. Key point: this is the largest volcanic system on Earth operating entirely underwater. The core positive feedback structure at mid-ocean ridges: one, initial perturbation, mantle upwelling beneath spreading plates at ridges. Plates pull apart, reducing pressure on the underlying mantle. That pressure reduction induces decompression. Melting generates basaltic magma, initiates upward heat and mass transport. This establishes the perturbation. Plate separation leads to mantle upwelling, which then leads to melt generation. 2. Pressure melt flow feedback, fundamental loop. Once melting begins, magma extraction reduces mantle density, buoyancy of upwelling, material increases, upwelling velocity increases, further decompression, melting occurs. So you get a self-reinforcing loop. Upwelling leads to melting, which leads to buoyancy increases, which leads to faster upwelling, and this leads to more melting. This is classic positive feedback operating continuously along the ridge system. 3. Thermal viscosity, convection feedback. As mantle temperature rises locally, viscosity decreases. Convective efficiency increases. Melt production becomes more efficient. That leads to higher temperature, which leads to lower viscosity, which leads to faster convection, which leads to enhanced melt transport. This is directly and analogous to the mantle side feedback that emphasizes in the GTF model just at present day rates. 4. Crustal thinning and permeability feedback. As magma intrudes and erupts, new oceanic crust forms, fractured networks expand, permeability increases. Increased permeability allows hydrothermal circulation, efficient fluid penetration, continued thermal weakening. This reinforces spreading. Fracture leads to fluid flow, leads to cooling plus weakening, which then leads to continued spreading. Whoops. Um, right. Right. Latent heat dominance. The critical analog. This is where mid-ocean ridges become uniquely important. 5. Immediate magma-water interaction at ridges. Magma erupts directly into seawater. Lava quenches almost instantly. Enormous thermal gradients drive phase changes. Energy is removed via latent heat evaporation, water to steam, that is, latent heat fusion, lava to solidification, that is, and convective heat transport into the ocean. A temperature rise is capped because energy goes into phase change, not heating. 6. Hydrothermal circulation as a heat pump, cold seawater penetrates deep into newly formed crust, is heated by magma, rises and vents at black smokers. This creates a self-sustaining cooling feedback. Magma heats water, which leads to water circulation faster, which leads uh, circulating faster, which leads to water removal increasing, which led magma cools without overheating surroundings. Important: higher heat flux, stronger circulation, more heat removal. That is cooling that scales with heating, not against it. So in other words, it's thermally driven. 7. Why this is still a positive feedback loop system. Critically, cooling does not shut down ridge volcanism. Spreading continues, melt generation persists. So we have positive feedback in mantle melting and upwelling, and negative feedback in temperature via water mediating cooling, operating simultaneously. Some negative feedback loops may be mixed in, but the overall result is a positive feedback loop which generates conditions that may cause a negative feedback loop as well. Why this is the strongest analog for flood-water interaction. Mid-ocean ridges show empirically that water-dominated heat sinks can handle enormous heat flux. Earth loses most of its internal heat through submarine volcanism today. Latent heat removal can dominate over radiation. Heat is removed into the oceans long before it ever reaches the atmosphere. Higher heat flux activates stronger cooling automatically. No fine tuning required. Fluid physics enforces it. Positive feedback can persist under heavy cooling. Mantle and 8. Mantle melting and spreading continue despite intense heat removal. All right, scaling this conceptually toward the flood conditions. Under flood conditions, you would expect orders of magnitude more water coverage, global synchronization of ridge-like volcanism, much higher convection velocities, vastly increased hydrothermal and steam generation capacity. Mid-ocean ridges demonstrate the direction of the physics. More heat led to more transport, led to more water interaction, which then led to more effective heat removal. The GTF model proposes that the flood simply pushes the same system into a far more catastrophic and energetic regimes. Conclusion: mid-ocean ridges demonstrates that the mantle-driven positive feedback in melting and convection can coexist with dominant latent heat removal through submarine volcanism and hydrothermal circulation, preventing surface thermal runaway. Also, even volcanoes underwater, which all volcanoes at the time of the flood would have been underwater eventually, would still present the same GTF system positive feedback system while erupting underwater. All right, here's another example of an underwater volcanic system here. Hunga, Hapa 2022. Okay, this is what erupted in 2022. Basic facts: establishing the event, location Tonga, Kermadec submarine zone, SW Pacific, volcano type submarine Caldea volcano, water depth above vent 150 to 200 meters, eruption date January 15, 2022, so this is not too long ago, climatic phase. Eruption style: ultraviolet, phreatomagmatic, energy release comparable to tens of megatons TNT. Plume height 55 to 58 kilometers. Mesosphere, water vapor injected. Record breaking atmospheric H2O. Shock waves circled the globe multiple times. Wow. Key point: this was not an eruption. Underwater, it was an eruption where water magma interaction became the dominant driver of escalation. The positive feedback loop at Hunga Tonga. One, initial perturbation, magma intrusion into shallow seawater. Magma rose into shallow submarine environment where external water was unavoidable. Initial interaction caused rapid quenching of magma surfaces, steam generation, fragmentation of magma. This fragmentation did not damp the eruption. Instead, it sets up a feedback. Two, magma water fragmentation feedback core loop. As magma contacted seawater, water flashed to steam. Volume expansion shattered magma. Fragmentation increased surface area. Increased surface area caused more efficient heat transfer. More heat transfer caused more explosive boiling. That is classic positive feedback. Fragmentation led to heat transfer. Steam generation lead to more fragmentation. Instead of stabilizing the system, water amplifying the eruption. Okay, three, conduit excavation and pressure release feedback. Each explosive phase excavated more of the volcanic edifice, remove confining materials, allow deeper magma to rise faster. So explosion, leads to pressure reduction, leads to faster magma ascent, leads to a larger explosion. This loop continues until the climatic event. Four, thermal runaway without temperature runaway. Uh, Here's the subtle but critical point. Enormous thermal energy was released, yet temperature did not rise catastrophically. Energy was partitioned into latent heat, evaporation, mechanical work, shock waves, plume lofting, atmospheric injection. This demonstrates positive feedback in energy transfer, not temperature. That distinction is absolutely central to GTF model framing. Five, atmospheric coupling as a secondary feedback. The eruption injected massive water vapor, ash, and aerosol surface sulfur species. This caused radiative effects, mesospheric disturbances, climate relevant perturbations. The stronger the eruption became, the higher the plume, the greater the atmospheric coupling, the more energy redistributed away from the crust. Again, amplification, increased transport, not local heating. Why Hunga Tonga is uniquely relevant to GTF reasoning. This example is extremely important for three reasons. One, water can amplify volcanism. A common objection is water cools magma, so it stops volcanism. Hunga Tonga proves the opposite. It's often true. Water can increase eruptive efficiency and energy release through feedback. There is no need to understanding. There is a need to understanding this exact distinction. Two, latent heat can dominate energy partitioning at Hunga Tonga. Most energy went into phase change and transport, not into heating and surrounding crust or ocean. This is a real world demonstration of the effective heat removal versus final radiative removal distribution within the GTL model. This would mean at Hunga Tonga, most eruptive energy was absorbed into latent heat and mechanical transport rather than raising local temperatures, demonstrating how effective heat removal can precede slower radiative loss to space. Three, scaling toward flood conditions. Hunga Tonga represents a localized shallow water system with limited magma volume, yet it still entered runaway feedback. Under flood conditions, you would expect vastly more water, vastly more simultaneous vents, vastly higher magma flux, global synchronization. Hunga Tonga shows the direction of the physics, not the final magnitude. All right, conclusion. The 2022 Hunga Tonga Hunga Ahapa eruption, if I pronounced that correctly, Ahapa eruption demonstrates that magma-water interaction can produce a positive feedback loop in which fragmentation, steam generation, and pressure release uh, amplify eruption intensity, while latent heat dominates energy removal. This also shows a clear example of what I mean by effective removal of the heat, versus final removal. The heat is removed in a way and fast enough without relying on the speed at which it radiates to space and without catastrophic results in the ocean, waters, or the crust. All right, we're going to do another underwater eruption. This one's going to be Surtsey, 1963 to 1967. The eruption of Surtsey between 1963 and 1967 offers a rare and invariable natural experiment, a volcanic system that was observed from its very beginning and tracked through every stage of its evolution. Unlike ancient eruptions reconstructed from rock layers, Surtsey allows us to watch in real time how magma interaction with water can drive step-by-step amplification of volcanic activity through positive feedback processes. Because the eruption began entirely underwater and transitioned naturally as conditions changed, it provides a uniquely clear example of how volcanism can intensify while powerful cooling mechanisms operate simultaneously, making it an ideal capstone case for understanding feedback-driven volcanism and its relevance to large-scale catastrophic scenarios. Basic facts. Location off the south coast of Iceland. Tectonic setting, Mid-Atlantic Ridge. Submarine rift zone. Eruption starts November 1963. Eruption end June 1967. I did want to, when I did all this, I did want to include modern day examples of eruptions. I didn't just want to include ancient examples or something like that. I wanted to be able to include present day examples to show that these processes are actually observed in the present. So this is not just, this is evidence, but it's also evidence from what we know about these kinds of conditions involving volcanic eruptions. Eruption in June 1967. Water depth at start 130 meters. Initial style fully submarine, Fretto magnetic. Later styles subbarial, effusive, basaltic. Result formation of a brand new volcanic island. Key feature entire sequence directly observed and instrumented. Key point Surtsey lets us watch a volcanic system transition through feedback regimes instead of inferring them after the fact. Stepwise positive feedback sequence at Surtsey. Initial perturbation, magma intrudes into shallow seawater. When magma first arose beneath Surtsey, it encountered cold seawater under modest pressure. Water flashed to steam. Explosions fragmented magma violently. This was not stabilizing, it was amplifying. Magma water fragmentation feedback entirely runaway phase. Early Surtsey eruption were dominated by classic hydro volcanic feedback loop. Magma contacts water, water flashes to steam, steam's expansion fragments magma, fragmentation increases surface area. Increased surface area enhances heat transfer. More water flashes steam, so the loop was fragmentation, heat transfer, steam generation, more fragmentation. This is a pure positive feedback, and it intensifies until something changed physically. Three, conduit excavation and pressure release feedback as explosion continued. The vent widened, overlying water was displaced, confining pressure decreased. Deeper magma rose more easily. That produced a second reinforcing loop. Explosion pressure cut a reduction, faster magma descent, stronger explosions. Importantly, water did not suppress volcanism, it drove it. Four, latent heat dominance during peak activity during hydrovolcanic phase. Enormous energy went into vaporizing seawater, not into heating the ocean bulk, not into melting surrounding crust. Temperature stayed bounded because energy was absorbed by phase change and mechanical work. This is effective heat removal in real time, not theoretical modeling. 5. Automatic saturation. Transition to effusive volcanism. Here's where Surtsey becomes uniquely powerful. As volcanic debris accumulate, a tough ring grew. The vent became isolated from seawater. Magma water interaction decreased. Once water access dropped, hydrovolcanic feedback shut down. Eruption style transition to effusive lava flows. The system self terminated its feedback loop by changing boundary conditions. No fine tuning, no external intervention. 6. Cooling mechanisms never stopped eruption. Throughout the entire sequence, water was removing heat efficiently. Steam plumes carried energy upward. Lava entering water quenched instantly, yet volcanism persisted for nearly 4 years. Magma supply continued. Island growth accelerated into feedback shifted regimes. Cooling bounded sequences. It did not stop actively. Conclusion. Surtsey provides a fully observed example of a hydrovolcanic positive feedback loop, positive feedback, where magma water interaction amplified eruptions intensified, while latent heat removal bounded temperatures and the feedback naturally shut down as boundary conditions changed. Okay, now we're going to shift gears here to Deacon traps. Okay, basic facts, establishing the event, location, western and central India, type, large igneous provinces, also known as LIPs, flood basalts, age, according to secular timeline, 66 million years, according to that, near uh, KPG boundary. Um, duration, according to secular timeline, zero point 0.5 to 1 million years with intense pulses. Flood age and duration, mainstream geology assigns volcanism to 66 million years and spreads it over zero point 0.5 to 1 million years based on Unitarian assumptions. Flood models reinterpret the same volcanic sequences as rapid high flux eruptions occurring during the late stages of the flood and or immediately after, consistent with catastrophic tectonics and accelerated mantle processes. Additionally, these eruption occurred during the late flood and continued following the flood, according to the timeline of the flood. Erupted volume 1 to 2 million kilometers cube. Basalt originally more. Eruptive style predominantly fissure fed, effusive. Magma temperature hotter than normal, typical morb. Um, Likely driver mantle plume plus lithospheric extension. A key point: it was not a single eruption; it was a continent-scale volcanic system operating through repeated, self-reinforcing episodes. The positive feedback structure in the Deacon traps: one, initial perturbation, anomalously a hot mantle plus lithospheric stress. The Deacon event began with a hot mantle source, plume-related lithospheric extension and weakening, elevated geothermal gradients. This combination displaced the system from equilibrium by increasing melt production potential, lowering mantle viscosity, priming large-scale magma ascent. This satisfies the initial perturbation requirement for feedback. 2. Pressure melt eruption feedback core loop. As eruptions began, magma was extracted upward. Lithospheric pressure over the source region decreased to compression. Melting increased. Melt supply increased further, so the loop was eruption pressure reduction, more melting, more eruption. This is the same structural feedback as Lakey, but scaled from tens of kilometers to millions of kilometers squared. 3. Thermal viscosity convection feedback as heat accumulated at depth. Mantle viscosity decreased. Convective flow became more efficient. Melt transport accelerated. That produced higher temperature, lower viscosity, faster convection, enhanced magma delivery. 4. Lithospheric weakening and transport efficiency. Repeated magma intrusion thermally softens the lithosphere, widen fractured and dike networks, localize eruptive pathways. This caused easier magma ascent, higher eruptive frequency, further weakening. This is a self-reinforcing parameter evolution, one of the clearest criteria for positive feedback. While the deaking traps did not cause permanent thermal catastrophe, this is where critics often stumble. 5. Advective heat transport dominates conduction in the deaking traps. Heat was removed primarily by magma flow, not conduction. Lava was transported to the surface efficiently. The crust did not need to heat catastrophically to transmit energy. This is exactly the advective heat removal principle central to this model. 6. Atmospheric and surface cooling mechanisms. Despite enormous heat released, the Deakin eruptions injected massive SO2 and aerosols, increased cloud formation, altered planet albedo, caused climate cooling episodes between eruptive pulses. So once again, the massive volcanism coincided with cooling, not runaway warming. This mirrors Tambora, but sustained over longer times. Hydrologic and latent heat interaction. While not submarine, Deakin volcanism interacted with rainfall, surface waters, wetlands, groundwater systems. Lava water interaction produced steam generation, latent heat absorption, enhanced fragmentation in some phases. Not flood scale, but mechanically the same. 8. Saturation and termination by constraints. The Deakin system eventually shut down because plume flux waned, lithospheric conditions changed, plate motion carried India away from the source. This is finite saturation, not failure of feedback physics. Conclusion. The Deakin traps show that the pressure release, melting, temperature dependent mantle viscosity, and advective magma transport can sustain continent scale positive feedback volcanism while cooling mechanisms limit the thermal consequences. We're going to make do the conclusion for our evidence for the positive feedback loops. All right. Broad range of documented volcanic systems, including fissure-fed eruptions of Lakey, the climatically significant explosive volcanism of Mount Tambora, the long-lived mantle upwelling of the Hawaiian hotspots, the latent heat-dominated heat flux at mid-ocean ridges, the hydrovolcanic amplification observed at Hunga, Hapa, the continent scale pressure melt feedback characteristics of the Deakin traps, and the fully observed stepwise evolution of Surtsey demonstrates that positive feedback loops are a well-established features of volcanic systems across a wide range of spatial and temporal scales. In each case, amplification of volcanic activity is accompanied by efficient heat redistribution through advective transport, phase change processes, and atmospheric coupling, preventing catastrophic thermal accumulation despite high energy flux. Collectively, these examples show that positive feedback in geologic systems does not entail thermal runaway, but rather operates within physically bounded regimes, providing empirical support for models in which intensify heat transport and cooling mechanisms scale together and naturally terminate as boundary conditions change. Together, these examples establish that the physical components within the model, amplification of heat transport, dominance of heat of latent heat, of latent and advective cooling, and natural saturation by changing boundary conditions are not speculative constructs, but well-documented behaviors of real volcanic systems operating at different scales. All right, also provide some sources here. Um, According to the MFCI model, the explosive interaction needs an initial crude mixing of the magma and water on the scale of 1 to 10 centimeters. Length dimensions of water dominance, where a form or vapor film forms a stable boundary layer between the magma and the water. The film can become unstable and from an external pressure pulse or local expansion and collapse across the mixing volume, leading to thermal coupling and high instantaneous heat transfer between water and magma. The high heat transfer leads to superheated and rapidly expanding water, which cannot culminate by the cooling magma that forms brittle stress cracks. The water intrudes into the cracks, causing further superheating, expansion, pressurization, and crack propagation in a positive feedback loop that finally produces a thermal detonation. The explosive energy is released as thermal hydraulic shock wave. The efficiency of the process is partly determined by the efficiency of the initial magma water mixing, as well as elastic properties of the magma during the brittle stress wave propagation. That is the source right there at the bottom. Here's another quote. Open and closed system degassing feedbacks have a strong controlled magma ascent and eruptive style. For open system degassing, the release of volatiles will decrease the buoyancy and overpressure of the magma, leading to slower ascent and allowing more time for equilibrium, degassing, and outgassing. Crystallization and viscosity increases enhance this positive feedback, and left unchecked, this will normally, can't really see that. I kind of blocked it there. To slow decompression rates, thus diminishing the likelihood of overpressure buildup and leading to effusive eruptions. However, negative feedbacks can also occur to counteract the loss of volatiles, which may lead to more explosive eruptions. The added buoyancy from volatile exo solution and bubble expansion will drive faster ascent, making outgassing less efficient, which may lead to disequilibrium degassing. This positive feedback is further enhanced by nucleation of small bubbles, which may limit bubble coalescence. In addition, for more silicate magmas or when decompression rates are high enough, decompression induces crystallization will be suppressed. This may have two effects. First, it keeps the viscosity low to enable faster ascent, and second, it provides less bubble nucleation uh, uh, sites and thus keep potential for outgassing. For some non-Newtonian magmas, excess deformation of the uh, leads to shear thinning behavior, degassing, viscosity, and thus further increasing ascent rate. These feedback promote more explosive behavior. Here's the source there at below. Here's another quote. Following large central vent eruptions that drain the chamber and release accumulation over pressure, both regional and magma eruptions could return to proximal areas as efficient chamber volume and Vitoric stresses are reduced. All right, there is a positive feedback between recharge, pressurization, and magmatic lensing efficiency. A dike recharge event will increase stresses around the magma chamber at fixed volume, which in turn enlarge the capture zone and cause increased influence on subsequent rising dikes. All right, we're gonna look at some volcanic evidence within the sediment of the flood layers and showed that there's evidence of volcanic activity during the flood. Massive volcanic evidence during the flood. Laterally extensive cave bennetites, altered volcanic ash interbedded in marine limestones and shells, or Dolphin. If I'm not mistaken, I believe that's a layer, flood layer here. These are thin, thick, regionally traceable clay beds that begin as airfall ash settling into seawater. Their wide lateral continuity and repeat occurrence record multiple large explosive eruptions. Sorry. Explosive eruptions during ongoing sedimentations, not a one-off event. The Daki and I'm not used to reading those words, so if I mispronounce it, forgive me. Daki and Millbrig K. Bennetites, again Ordovcian, as continent scale marker beds. These two ash beds are famous because they can be correlated across large areas, consistent with very large explosive eruptions that produce enormous ash clouds. Their preservation inside marine strata means volcanism was active during deposition of these layers. Clusters of ash beds, three clusters of ash beds, not just single beds, in flood Paleozoic sequences. In several basins, ash beds occur as stacked sets separated by ordinary marine sediments, evidence of repeated eruptive pulses, not an isolated eruption. In flood term, that is consistent with sustained volcanism through an extended portion of the depositional sequence. DVN ash beds in major shell and limestone packages, e.g., Tioga ash bed intervals. These are widely recognized ash bed horizons within Devonian strata, commonly included black shells in some regions. Their position as distinct beds inside the sediment pile is direct evidence that explosive volcanism occurred while these sediments accumulated. Cretaceous bentonite marker beds in marine shells, e.g., Maury shell, uh, clay spur bentonite. Some Cretaceous marine shell packages include laterally continuous bentonite layers used as stratigraphic markers. A marker bentonite is not volcanic influence in general, but a discrete ash fall preserved in place, again showing volcanism during deposition. Dozens of altered ash beds in continental lacustrine systems, Jurassic, Morrison, Bushy Basin member. Parts of the Morrison are well known to be for being unusually rich in altered ash, often converting in Semitic clay. Multiple discrete ash beds preserved in fluvial lustrine strata imply frequent ash falls into surface water and wet sediments during deposition. All right, 7. Pillow lavas as a diagnostic indicator of lava erupting into water. Pillow lava morphology forms when basaltic lava erupts into water and rapidly quenches. Finding pillow lavas interlayered with sediments is direct evidence as of subaqueous volcanism in water-covered environments. Um, Haloclastite volcanic glass breccia formed by quench fragmentation in water. When hot water lava hits water, it can shatter into glassy fragments, producing haloclastite in stratified succession records intense lava water interaction, not slow subaerial well, how do you pronounce that? Subaerial lava cooling. Um, Circean style tuffs Remember Surfacean style tuffs. Ferromagmatic deposits indicating explosive magma-water interaction. Circean deposits, tough rings or cones, embedded ash, and lapalli tuffs form when rising magma explosively interacts with shallow water. These deposits are textbook evidence that water amplified fragmentation and eruption energy. Volcaniclastic marine deposits. We work in ash, lapalli, and volcanic sand interbedded with normal marine sediments. Marine settings often preserve layers of volcanic debris transported in deposits underwater. Interbeds of volcaniclastic clastics among non-volcanic shells or limestones show repeated eruption input into to a water-dominated depositional system. Number 11, pepperite. Magma sediment mingling, breccia, indicating magma intruded wet, unconsolidated sediment. Pepperite form when lava or shallow intrusions mix with water, rich, unconsolidated sediment, producing a distinctive mixed rock. This is strong evidence for near contemporaneous sedimentation and volcanism because the sediment must still be soft and wet. Soft sediment deformation plus thermal effects at lava contacts, baked sediment, fluid escape, disrupted limitation. When lava advances onto wet sediment, you can get localized baking, steam-driven disruption, and deformation at the contact. These features show that sediments were still water-rich and not lithified when volcanic heat arrived. Lava flows interbedded with sediment layers, volcanism as episodes within the depositional sequence, where basalt flows occur between sediment layers and not nearly cutting across them. The simplest reading is that volcanic output was episodic during ongoing deposition, not exclusively before or after the sediment package. 14. Rift basin succession with interbedded lava now or flows and sediments, lava flows and sediments, e.g., camp related basalt in some basins. Some rift basins preserve repeated lava flows interlayered with lake and river sediments. This demonstrates that large area volcanism can occur in pulses while sedimentation continues. An architecture flood geologists often see as compatible with catastrophic tectonics. Thick ash-bearing intervals, tufaceous mudstones, siltstones, sandstones indicate sustained volcanic input. Not all volcanic evidence is a single ash bed. Sometimes sediment packages are persistent ash-rich, tufaceous, indicating that volcanism was not rare, but a continuous contributor to the sediment budget. Hydrothermal alterations, that's number 16. Hydrothermal alterations tied to volcanic glass and ash, palogotization, clay alteration, cement changes, volcanic glass in ash, and hyaloclastic readily alters to clays and secondary materials when exposed to water and heat. Widespread alteration of ash horizons is consistent with water-rich conditions during and after deposition, and it preserves the volcanic fingerprint even after diagenesis. All right. Across sediment successions, commonly interpreted as flood deposits, the rock record preserves repeated fingerprints of active volcanism. Widespread ash beds alter to bentonite, volcanic debris reworked into marine and continental sediments, pillow lavas, and hyaloclastic clastites formed by lava water interaction, and pepperites recording magma intruding wet unconsolidated sediment. Together, these features show that volcanic eruptions occurred repeatedly and at multiple scales while sediments were still being laid down, indicating intense volcanic operating alongside large-scale water-driven deposition. This would also include lateral extensive ash beds, altered benatites, volcaniclastic deposits, subaqueous lava textures, and direct lava sediment interaction features. These materials represent discrete eruptive events, repeated volcanic pulses, and sustained volcanic influence occurring contemporaneously with sediment deposition. Regardless of interpretive framework, the physical evidence demonstrates that volcanism was not peripheral to the formation of these strata, but an active and recurring process operating within water-dominated depositional environments. The presence of abundance of volcanic ash layers, subaqueous eruptive processes, volcaniclastic sediments, and lava sediment interaction features within flood assigned strata indicate that volcanism and sedimentation were closely coupled processes. These observations are consistent with scenarios involving widespread volcanism interacting with extensive surface waters where heat, mass, and energy were rapidly redistributed rather than locally accumulated. As such, the geologic record itself supports the plausibility of feedback dominated volcanic systems operating during the large scale catastrophic deposition. The rock record contains clear evidence that volcanism, often explosive, often water interactive, occurred repeatedly during the deposition of strata commonly assigned to the flood, demonstrating that volcanic activity was a central, not incidental, component of these depositional systems. I'm not going to quote every quote here. If you all want to, y'all can pause it, take in the quote, look up the source. The source is there at the bottom. Um, it's just hard to go through the sources. The main thing about the sources is that it does show that there is agreement in the peer review literature, because I actually used academic sources for this. So this is not something from Wikipedia or anything like that. They're from peer review sources and that sort of thing. So y'all can take read it, look the source up, etc. Here's some more sources. Again, it supports that this is occurring during the flood layers. Convection and advection. Um, we're going to be doing that section next, starting with convection and then moving to advection. Of course, we're going to be talking about this relevance to my model. These are important mechanisms that are used in my model, so pay attention. If you really want to understand my model, this is going to be really, really important, including for critics, um, to understand what's going on here as well. Introduction in my model as accelerated nuclear decay, and for short, heats up the mantle. Mantle convection speeds up. This happens because temperature gradients are steepened, Rayleigh number hits critical thresholds, buoyancy of the mantle increases, viscosity decreases, and mantle plumes regions of the mantle that are hotter than the surrounding mantle, and so it rises faster. It is also believed to be one of the major triggers for volcanic eruptions. Talking about plumes rise faster due to their own buoyancy being increased. This high-speed convection then triggers high-speed advection in the crust, pulling the heat crustal rock into the upper mantle. This model's system is not only a positive feedback loop, but it's thermally driven or driven by the heat. This high-speed convection is what launches this thermally driven positive feedback loop system. In this section, we will be given give the evidence for this effect on mantle convection and advection, which is also being used by this model to bypass conduction in removing this heat generated in the crust from things like runaway subduction, the CPT model, or heat generated from meteor impacts, etc. And so all of this is going to be all this heat in the crust is going to be advected into the upper mantle. Um, the advection is my primary mechanism for getting the heat out of the crust. The three mechanisms that I use to bypass conduction. Um, Now it doesn't reduce it to irrelevancy. Conduction still happens. It's just the fact that most of this heat, intensified heat, is being removed via these three mechanisms, which are convection, advection, and of course volcanism. Um, but that to remove it from the earth, that is. But uh, the convection is heated up as a result. Mantle convection is heated up. This is the flow of heat in the mantle. It's heated up as a result of solar nuclear decay. Heating it causes it to increase, and the increase of convection then triggers high-speed advection in the crust, which removes the heat to the upper mantle. And this is going to be talked about as we move forward. All right, let's talk about convection. Mantle viscosity drops strongly as temperature rises. Arrhenius type rheology. We'll discuss rheology in my next video. We're going to be discussing it more specifically. It's actually a branch of physics because we're responding to a particular criticism that tries to argue a particular position, and that position ignores the way rheology is, but we'll get into that in the next video, which necessarily increases convective velocity. What scientists mean by this? The mantle's resistance to flow viscosity depends exponentially on temperature. Hotter mantle deforms much more easily. Like I said, we'll be talk about rheology next video, and that's going to be important. Why that speeds convection for the same buoyancy driving lower viscosity means less resistance, so flow accelerates. How we know, real evidence, laboratory rock deformation experiments on olivine and mantle analogs repeatedly shows strain rate rises steeply with temperature at fixed stress. Conversely, effective viscosity drops steeply as temperature increases. This temperature viscosity dependence is one of the most robust results in mantle rheology. Real world signatures, hot, quote unquote, hot regions inferred from seismic tomology, low seismic velocities, lined with regions of active upwelling and plumes and high volcanism, e.g., Hawaii, Iceland, consistent with hot, weaker mantle, permitting faster ascent and flow. Buoyancy driving increases with temperature anomaly. This is number two. Delta T, because density decreases as temperature increases. What scientists mean: thermal expansion causes hot mantle to be less dense. The buoyancy force scales with P times or rho times G times alpha times delta T. Why that speeds the convection? Larger delta T leads to larger buoyancy, leads to stronger driving, stronger driving, which leads to faster flow. All else equal. How we know? Thermal expansion is measured in mineral physics, density temperature relations for mantle minerals, and mantle assemblages are well constrained. Real world signatures, plume related swell topology, broad ocean uplifts, gravity anomalies, and dynamic topography correlate with inferred hot mantle upwellings. Buoyancy is physically required to support the observed uplift. Number three, convection strength scales with Rayleigh number, Rayleigh abbreviated with the variable Ra. Hotter mantle rises Rayleigh and therefore hotter rises Rayleigh and therefore rises convective vigor and heat transport. What Rayleigh captures. Rayleigh combines buoyancy, driving, and material properties. Larger delta T, larger layer thickness, lower viscosity, and higher expansivity all increase Rayleigh. Why higher Rayleigh implies faster convection. In convection theory and numerical mantle convection models, increasing Rayleigh increases convective vigor, stronger velocities, thinner thermal boundary layers, higher heat flux. How we know laboratory convective experiments in fluids show transitions from the conduction dominated heat transfer to convection dominated heat transfer once Rayleigh exceeds a critical value, also known as Rayleigh critical. By the way, Rayleigh critical is identified by the variable RAC. So RAC, RA for Rayleigh, and then C for critical. But if you see RAC, that means Rayleigh critical. Um, Numerical mantle convection studies reproduced the same behavior. Above critical Rayleigh, convection organizes into cells and plumes, and convective heat transport rises strongly. Real world signatures, Earth's mantle is widely treated as having Rayleigh far above critical, consistent with the fact that conduction alone cannot explain observed surface heat flow and tectonic volcanic activity. Number four, convection dominates heat transport in hot interior settings because boundary layers thin as Rayleigh increases, steeper temperature gradients in the boundary layers. What scientists mean? Higher Rayleigh convection produces thinner thermal boundary layers. The temperature drop is concentrated across thinner layers, making gradients steeper there. Why heat makes this stronger? Heating larger delta T and lower viscosity both increases Rayleigh, which thins boundary layers and increases heat flux. How we know convection experiments and scaling laws show boundary layer thickness decreases as Rayleigh increases. Models of mantle convection reproduce thin lithospheric boundary layers and strong gradients near the surface and at the base of the mantle. Real-world signatures, oceanic lithosphere cools rapidly away from ridges, steep near surface gradient early on, and or thickens with age. This behavior is consistent with a convecting mantle supplying heat to a thin conductive boundary layer rather than a purely conductive interior. Number five, mid-ocean ridges provide direct, measurable evidence that hotter upwelling mantle produces stronger melt generation and higher magmatic throughput, consistent with more vigorous convection. What's observed? Ridges are where mantle rises and decompresses. A higher mantle potential temperature increases melt fraction and crustal thickness and elevates magma supply. While that links to faster convection, higher temperature reduces viscosity and increases buoyancy. Both promote stronger upwelling and melt extraction itself enhances buoyant transport. How we know? Ridge bathymetry, crustal thickness, seismic refraction, and geochemistry constrain variations in mantle temperature and melt supply. Hotter ridge segments and plume ridge interactions show enhanced volcanism and thicker crust. Real world examples: Iceland is a ridge plume interaction zone with anomalous high magnetism compared to quote unquote normal ridge segments, widely interpreted as hotter mantle and enhanced upwelling. Number six, plume systems show that hotter, more buoyant mantle rises faster and more effectively. Plume buoyancy produces vertical flow sufficient to generate hotspot chains and large volcanic edifices. What's observed: long-lived hotspot tracks, Hawaii, and plume-related flood basalts, e.g., Deacon, talking about the Deacon traps, Siberian traps, in mainstream interpretations, require sustained upwelling and large melt supply. Why it implies speed up with heat. Plumes are thermal anomalies. Larger temperature anomalies produce greater buoyancy and lower viscosity, both of which increases ascent speed and melt production productivity. By the way, plumes are literally regions of the mantle. Mantle plumes are regions of the mantle that's hotter than its surrounding mantle, so essentially it rises faster in the mantle. How we know tomographic images, low viscosity, hot quote unquote hot columns. Geoid topography anomalies indicate buoyant support. Geochemistry indicate deep hot source components. Physical plume models show ascent velocity increases with buoyancy, flux, and decreases with viscosity. Um, real decreases with viscosity. Real world examples: Hawaii and Iceland are the standard observational anchors. Persistent volcanism, swelling, and seismic low viscosity anomalies consistent with hot upwellings. Number 7, post-seismic and post-glacial responses show that when mantle is effectively quote-unquote weaker, lower viscosity flow responds faster, supporting the principle that lower viscosity increases convective creep velocity. What's observed: post-glacial rebound rates, constrained mantle viscosity. Lower viscosity implies faster rebound, faster flow response. Post-seismic viscoelastic relaxation similarity constrains asthenosphere viscosity. Lower viscosity implies faster deformation and stress relaxation. Why it matters: temperature is a primary control on viscosity. Regions with hotter asthenosphere behave more weakly and respond more rapidly, consistent with the temperature viscosity velocity linkage. How we know: uplift time series, GPS, tide gauges, geologic shorelines, and post-seismic deformation time series can be inverted for velocity structure. Real-world examples: rapid rebound in formerly glaciated regions implies a relatively low viscosity upper mantle slash asthenosphere compared to colder high viscosity mantle. Okay, number 8, thermal runaway is not required for speed up. Modest temperature increases can produce large viscosity drops and thus large velocity increases. Key physical point: because viscosity depends exponentially on temperature, even a few hundred degrees can change viscosity by orders of magnitude depending on activation energy and water content. Why that strengthens the case: you don't need an implausible temperature spike to get major changes in flow speed. Mantle rheology is inherently nonlinear in temperature. How we know: this comes directly from experimentally constrained laws and is built into essentially all model mantle convection simulations. Real world examples: the asthenosphere, hotter, weaker, enables plate motions and decoupling relative to colder lithosphere. Plume heads, hotter, generate anomalously high melt volumes relative to ambient mantle. Number 9, convection produces characteristic heat flow patterns that conduction cannot reproduce, indicating that convective transport is the controlling regime in the mantle. What's observed: global surface heat flow is high in technically active zones, ridges, hotspots, and lower in stable cratons. These patterns fit a convective mantle with boundary layers. Why it ties to speed up with heat, higher temperatures and lower viscosities in upwelling regions correspond to higher heat flux and volcanism. In convective scaling, higher Rayleigh implies higher convective heat transfer. How we know heat flow measures plate cooling behavior and mantle topography together require a convective mantle supplying heat to the lithosphere. Conduction alone from a static interior does not match observed spatial patterns. 10. Critical Rayleigh number, onset of convection, provides a hard physical threshold. Once surpassed, heat transfers hits from conduction dominated to convective dominated. This is in literature, by the way. If you follow the equations and the arguments that are made in peer-reviewed literature, they actually argue for this. Convection dominated, and vigor increases with further heating. What scientists mean, below critical Rayleigh, a layer remains stable and transfer heat mainly by conduction. Above it, buoyant overturns begins. While this supports the point, increasing internal heating, or delta T, can move the system further above critical, increasing convective rigor and decreasing the role of conduction in the interior. Simply put, the higher it is, the more it's going to move from conduction only to convection only. Under a certain threshold, it is considered conduction dominated. But then when you get above that threshold, it then becomes convection dominated. All right. How we know this is the among the most replicated results in fluid dynamics. It's demonstrated in countless lab experiments and is foundational in geophysics. Real-world application, Earth's mantle is treated as strongly supercritical Rayleigh or leads to Rayleigh critical, consistent with observed tectonics, volcanism, and heat flow. Okay, number 11. Hotter mantle leads to more melt is observed. More melt leads to more buoyant transport is physically together. They reinforce faster upward motion in hotter regions. What's observed, higher mantle temperatures correlate with larger degrees of partial melting inferred from crustal thickness and basalt chemistry. White implies faster motion, melt extraction, and retain melt reduced density and can lower effective viscosity in partially molten regions, aiding transport and focusing flow. How we know petrology and geochemistry constrain mantle potential temperatures and melt fraction. Seismology detects partial melt zones as low viscosity regions. Real world examples, plume influence, ridges, Iceland, and hotspots show enhanced melt production and sustained volcanic output relative to ambient mantle. Number 12, thermal boundary layers at the top and bottom of the mantle steepen with increased convective vigor, produce stronger contrast that further drive buoyancy. What's meant in vigorous convection, hot upwellings and cold downwellings become more distinct. The system organizes into a stronger thermal anomalies. Why it matters, stronger anomalies mean stronger buoyancy forces and faster flow. This is a feedback in convective organization. How we know convective models show that as Rayleigh increases, plume becomes thinner and faster, and temperature contrasts concentrate into narrower structures. Real-world examples: narrow plume conduits imaged beneath hotspots, low seismic velocity columns are consistent with plume organization expected in vigorous convection regimes. Convection summary. Mechanistic evidence, physics, why heat speeds convection, temperature dependent viscosity, mantle viscosity decreases exponentially with increasing temperature, Arrhenius rheology, allowing much faster flow under the same driving forces. Buoyancy scales with temperature anomaly delta T. Hotter mantle is less dense. Increased delta T directly increases buoyant driving forces that accelerate convection motion. Rayleigh number scaling higher internal temperatures increases Rayleigh by increasing buoyancy and lowering viscosity. Higher Rayleigh produces stronger and faster convection. Stronger, faster convection. Critical Rayleigh threshold. Once Rayleigh exceeds the critical value, heat transfer shifts from conduction dominated to convection dominated behavior. Buoyancy layer thinning increases Rayleigh produces thinner thermal boundary layers, concentrating temperature drops into steeper gradients and enhance heat flux. Non-linear amplification, because viscosity depends exponentially on temperature. Modest heating can produce large increases in convective velocity. Plume acceleration with heat. Hotter thermal anomalies generate stronger buoyancy flux, causing plumes to rise faster and much more efficiently. Okay, we're going to start talking about advection now. Um, one advection is the real heat mass transport in the crust, because the crust, when hot or weak, can move as the forming solid, not just conduct heat. What scientists mean, advection is the transport of heat and material by bulk motion flow of rock, melt, or fluids. As distinct from conduction in the crust, it often means ductile lower crust of low and or melt bearing flow. This, in the modern context, this actually happens in the modern world, but it usually happens with the lower crust, which is much more ductile than the upper crust. However, during the flood, the entire crust would have been very ductile as a result of accelerated nuclear decay. How we know it occurs, field lab and geodetic data shows that at sufficiently high temperatures, and especially with partial melt, lower crust behaves viscously and can move laterally and vertically. Uh, uh, Real world examples or applications: lower crustal shear zone, migmatite terrains, and nice, I guess that's pronounced nice. Domains demonstrate crustal material was physically transported while hot. 2. Hot crust becomes weak enough for rapid ductile flow. Viscosity collapses with temperature and melt, and enables high-speed lower crust channel flow. What scientists mean, when lower crust approaches or exceeds the solidus, a small melt fraction can reduce effective viscosity dramatically, turning the lower crust into a mechanically weak layer capable of fast flow. How we know it occurs: laboratory rheology plus petrologic constraints show viscosity is stronger, strongly temperature dependent. Melt bearing rocks weaken substantially. Real world examples: high grade metamorphic belts with abundant migmatite and granitic melts record large strains accumulated while the crust was hot. 3. Deep crustal flow is directly observed indirectly through GPS and INSAR as rapid post-seismic and interseismic for deformation that requires ductile lower crustal motion. What scientists mean, after major earthquakes, the lower crust and upper mantle relax by viscous flow, producing measurable surface motion over months to years. How we know it occurs: time-dependent ground deformation observed by geodesy cannot be explained by elastic rebound alone. It requires viscous flow beneath the brittle crust, i.e., effective motion of material. Real world examples, large subduction, earthquakes, and continental strike slip systems show post seismic transients consistent with lower crust and upper mantle flow. Number four, high heat flow provenances show that conduction alone cannot redistribute heat fast enough. Advective transport by melt or fluids and moving rock must contribute. What scientists mean in regions with extreme heat flow, heat is carried upward by magma movements, hydrothermal circulation, and ductile flow. How we know it occurs, thermal budgets and observed gradients often demand faster transport than conduction can provide over short periods of time. Real world examples of volcanic arcs, rifts, and geothermal fields are dominated by advective heat transport through magma and fluids. Number five, magma itself is an advective conveyor belt. Repeated dike and seal injection moves hot material rapidly through the crust. What scientists mean, magma ascent and lateral intrusion physically advect heat and mass, establishing pathway that can feed further transport. How we know it occurs, mapped dike swarms, seal complexes, and under plating layers show enormous volumes moved through the crust as discrete bodies. Real-world examples: flood basalt provinces and large igneous provinces show crustal scale pluming networks indicating rapid mass and heat redistribution. Number six, underplating and basal crustal heating can drive buoyant lower crustal flow back toward hotter regions and upward into domes. Advection is a deforming crust. What scientists mean, adding hot mafic magma at the crust's base heat and weakens it, promoting gravitational and pressure-driven flow. How we know it occurs, petrology records, basal heating and partial melting. Structural geology records large strains and vertical transport of hot crustal rocks. Real-world examples, metamorphic core complexes and gneiss domes reflect deep crustal material transport upward while hot. Number seven, subduction systems produce strong mantle corner flow that mechanically couples to the base of the crust and transports heat and material. What scientists mean, the mantle wedge circulates due to slab motion. This flow advects heat and exerts basal shear on the overriding plate. How we know it occurs, patterns of arc volcanism, seismic anisotropy, and wedge temperature constraints are required. Vigorous wedge flow um, requires a vigorous wedge flow. Real-world examples: volcanic arcs align with predicted wedge flow and thermal structure, indicating active advective transport in mantle and coupled lithosphere. Number eight, when the lithosphere becomes weak, mantle flow can directly reorganize it through delamination or drips, advecting dense lower crust or lithosphere downward and replacing it with hotter mantle. What scientists mean, gravitational instability removes dense lower lithosphere, hotter asthenosphere rises to replace it, rapid mass exchange across the moho. The moho is an invisible boundary. Um, uh, on that in the crust. Um, Seismic boundary. How we know it occurs. Seismic imaging, uplift patterns, volcanism, and geochemistry indicate lithospheric removal and asthenospheric replacement. Real world examples, regions with sudden uplifts plus volcanism consistent with lithospheric removal show that mantle dynamics can drive strong vertical transport. Number nine, uh, extensional uh, extensional province provinces demonstrate rapid lower crustal flow as the crust thins. Hot, weak lower crust moves laterally while the brittle upper crust faults. What scientists mean in rifting, the upper crust breaks while the lower crust flows, redistributing crustal thickness by advection of ductile material. How we know it occurs. Structural patterns require decoupling. Seismic and geodetic constraints show lower crustal flow beneath faulted terrains. Real world examples, basin and range type extension. Um, and metamorphic core complexes reflect deep crustal advection during extension. Number 10, orogenic plateaus show that a hot lower crust can flow for hundreds of kilometers. We distribute mass large scale advection dominated by geology and geophysics. What scientists mean, channel flow or distributed lower crustal flow, transport partially molten crust laterally beneath the stronger lid. How we know it occurs, plateau evolution, crustal thickness patterns, seismic low viscosity zones, and metamorphic histories require lateral redistribution. Real world examples Tibetan plateau models and observations commonly invoke large scale lower crustal flow to explain topography and crustal structure. Number 11, metamorphic pressure, temperature, time paths in exhumed rocks require rapid vertical transport of deep crustal material, advection of rock mass, in other words. What scientists mean, rocks formed at high speed or high pressure temperature must be moved upward through the crust to be exposed. That is physical advection of material. How we know it occurs, mineral assemblages constrain formation depths and temperature. Their presence exposure demands a substantial transport. Real world examples, high grade terrains and metamorphic belts show deep crustal rocks were advected upward along major shear zones. Heat is advective. Keep in mind that the type of advection I'm invoking, I think there's like three forms of advection, but the type of advection that I'm invoking here is essentially the weakened areas of the crust is actually flowing into the upper mantle. So the areas are getting weakened by accelerated nuclear decay as well as by uh, uh, high speed convection in the crust. This triggers advection in the crust and or high speed convection in the upper mantle, and this triggers high speed advection in the crust, and that causes this heated material, or at least the intensified heated materials. They're the most hot to flow down to the upper mantle. Okay, number 12, heat is advected upward and outward in plume influence lithosphere via melt transport and lithospheric weakening, increasing the efficiency and speed of crustal heat removal pathways. What scientists mean, hotter mantle increases melt production, melt transport advects heat, repeated intrusion weakens the lithosphere, allowing faster deformation and flow. How we know it occurs, plume prominences show increased magmatism, crustal modification, and thermomechanical weakening consistent with strong transport. Real world examples, Iceland and Hawaii demonstrate sustained melt and heat delivery and lithospheric modification consistent with strong advective components. Number 13, the brittle ductile transition migrates upwards as crust heats, enlarging the depth range that can flow, increasing the volume available for advective transport. What scientists mean, heating reduces strength and pushes ductile behavior to shallower levels, enabling faster bulk motion over a large thickness of a crust. How we know it occurs, metamorphic gradients and structural overprints show ductile deformation at shallower levels in hot regions. Geothermal gradients constrained the transition depth. Real-world examples: high heat flow regions show shallow ductile shear zones relative to cold cratons. Okay, number 14. Fast advection becomes unavoidable when transport timescales beat conductive timescales. High heat plus low viscosity plus strong driving forces yields bulk motion as the dominant response. What scientists mean: when the system is hot enough, adduction cannot keep up with the imposed thermal and mechanical gradients. Flow becomes the efficient pathway. Uh, how we know it occurs: measured thermal diffusivities implies conduction is slow over crustal distances. Observed rapid deformation and magmatic transport require bulk motion. Real-world examples: rifts, arcs, and plume provides repeatedly show that the fastest redistribution of heat and mass is by moving material, not by waiting for conduction. You'd be waiting forever for connection. All right, let's do the advection summary here. Mechanistic evidence, advection physics, why heat enables fast crustal transport. Advection is bulk transport. Heat and material are moved in by the physical motion of rock, melt, or fluids, not by mechanical or molecular diffusion, as in conduction. Temperature dependent weakening: as crustal temperature rises, rock viscosity drops exponentially, allowing the lower crust to behave as ductile flowing layer. Now, of course, that's it's identifying a summary of all this stuff as. So, in the modern context, the lower crust it's going to become more ductile during the flood. But in my model, the whole crust will be ductile in some extent because radioactive elements are actually scattered throughout the crust and throughout the upper mantle and lower mantle and that sort, or upper crust and lower crust, and of course in the mantle itself. And so when high-speed convection occurs in the mantle, this is going to trigger high-speed advection in the crust, and it's going to cause all this heated material to actually flow really, really fast into the upper mantle. So all of it is going to be ductile to some extent, or not all of it, but a lot of it is going to be ductile, including the upper mantle. Partial melt amplification: even small melt fraction drastically reduce effective viscosity, enabling rapid flow of lower crustal material. Expanded ductile zone heating shifts the brittle ductile transition upward, increasing the thickness of crust capable of advective motion. Pressure and density gradient, buoyancy and pressure differences drive flow. Once mechanical resistance is sufficiently reduced, mechanical coupling to mantle flow. Faster upper mantle convection increases basal shear and thermal input, promoting crustal deformation and flow. Timescale advantage: at high temperatures, advective transport redistributes heat and mass far faster than conduction can over crustal distances. Okay, observational evidence of the Earth: advection occurs in hot crustal settings, lower crustal flow zones, high grade metamorphic terrains, and major shear zones record large strains accumulated while crust was hot and ductile. Metamorphic core complexes, deep crustal rocks, were advected upward and laterally during periods of elevated heat flow. Post-seismic deformation, GPS and INSAR measurements show time-dependent surface motion requiring viscous lower crustal flow. Post-glacial rebound, rapid uplift rates dominate low viscosity mantle and lower crust, consistent with temperature weakening flow. Magmatic intrusion network, dike swarms, steel complexes, and under plating demonstrates rapid advective transport of heat and mass through the crust. Rift and extensional provinces, faulted upper crust overlies a flowing lower crust, showing decoupling behavior enabled by high temperature. Plume influenced lithosphere. Hot mantle regions show enhanced mantle transport, crustal modification, and thermal reorganization consistent with strong advective processes. All right, here's my conclusion on that. Mantle convection and crustal advection are not separate or competing processes, but mechanically coupled responses of a thermally driven Earth system. As temperature increases, mantle viscosity decreases, and buoyancy forces intensify, driving faster and more vigorous convection once the Rayleigh number exceeds its critical threshold. This transition marks a regime where heat transport becomes dominated by bulk motion rather than conduction. In turn, increasing convective velocity steepens thermal boundary layers, enhances heat flux and amplifies mantle lithosphere coupling, where heat flux into the crust is sufficiently high. The lower crust weakens, the brittle ductile transition migrates upward, and the crust becomes capable of large-scale ductile flow. At that point, advection becomes the dominant mechanism for redistributing both heat and mass within the lithosphere. Geologic observations from mid-ocean ridges and plume provinces to high-grade metamorphic belts, magmatic underplating, post-seismic relaxation, and large-scale crustal flow demonstrates that advection is a natural efficient consequence of intensified convection in hot Earth systems. Together, convection and advection form a coupled, self-consistent transport framework that explains how large amounts of internally generated heat can be rapidly redistributed without accumulating catastrophically in the crust. All right. When mantle convection accelerates, it fundamentally reorganizes the mechanical environment at the base of the crust. Faster mantle flow increases basal shear stresses and establishes strong dynamic pressures gradients at the MOHO. The MOHO is short for Mohorovic discontinuity, is the boundary between the Earth's crust and the mantle. It is not a physical quote unquote surface you could see, but a seismically defined interface where rock properties change abruptly. Moho is the seismically defined boundary between the Earth's crust and mantle, marking a sharp change in composition, density, seismic velocity, and mechanical behavior. While elevated heat flux reduces lower crustal viscosity by orders of magnitude. Under these conditions, the lower crust is no longer able to behave as a rigid boundary. Instead, it responds as a deformable, density stratified layer subject to gravity and imposed stresses. Dense, weakened crustal material is mechanically driven downward toward regions of lower pressure and greater stability in the upper mantle, not because it is hotter than the mantle, but because buoyancy support is lost and resistance to flow is minimized. Simultaneously, hotter, buoyant asthenospheric material rises to replace the removed lithosphere, producing rapid mass and heat redistribution across the crust mantle boundary. This process represents advection governed by force balance, density gradients, and viscosity reduction, not by temperature gradients alone. As a result, heat stored in crustal material is efficiently transferred into the mantle system and redistributed by convection, demonstrating that high temperature regimes naturally favor removal and redistribution of heat rather than long-term crustal retention. This is important for my model because my model is thermally driven, and that's one of the foundational elements of my model is that it is driven by the very heat that's being generated. Okay, you can see some graphics here. The convection and advection in the crust. All right. I can also end up quoting sources to you. You can take the time to pause it and read the source. Here at the very bottom, I've got the actual source where it comes from, but I quote from the source here directly. Um, and it shows that high convection, and that sort of thing is occurring in the crust, that sort of thing. It is also generated or excels, speeds up by heat. So the hotter the mantle is, the higher the convection, the rate of the flow of heat in the mantle. Okay, got some more quotes here. Citations. The figure two is obviously applying to the paper that it's from. You got the sources at the end. Be You can be able to sit there and copy all that down if you want to. If you want to look at the sources information, or just go directly to the source. Okay, here's another source. I just didn't really want to sit there and have to read off all the sources that I have. I've got sources in there that shows this happening, and studies that have been done and models that have been made on it. The models the interior of the Earth and the flow of convection and that sort of thing. Most of the critics do concede that heat does speed up mantle convection, so usually that's not really challenged that much. All right. Any realistic discussion of large-scale heat generation during the Genesis flood must account for where that heat is physically transferred and stored. The Earth's mantle, which comprises the vast majority of the planet's mass and volume, function as the dominant internal heat sink in the Earth's system, as immense heat capacity, temperature-dependent viscosity, and active convective circulation allows it to absorb and redistribute enormous quantities of thermal energy without catastrophic temperature rise. It's talking about the mantle as a heat sink here, because that's the most powerful heat sink on Earth. The mantle is what we're talking about right now. When crustal material is heated and mechanically weakened, thermally temperature or thermal and mechanical coupling across the crust mantle boundary enables heat to be transferred downward into the mantle where it is rapidly dispersed by convection. Within the geothermal feedback framework, the mantle is therefore not a passive backdrop but a central participant in heat removal, providing a physically plausible reserve capable of absorbing most of the internal generated heat during the flood year while preventing runaway thermal accumulation in the crust. All right, the mantle has an enormous heat capacity relative to the crust. What scientists mean, heat capacity scales with mass and specific heat. The mantle contains 84% of Earth's volume and 67% of its mass. In physics, a heat sink is determined by thermal capacity and energy redistribution efficiency, not by the absolute temperature of the absorbing reservoir. A heat sink is defined by its ability to absorb energy due to large heat capacity and effective heat transport, not by being cooler than the heat source at all times. Heat flows whenever a temperature gradient and a viable transport pathway exist. How we know seismic models and mineral physics constrain mantle composition and mass. Calorimetric measurements constrain specific heat of mantle minerals in thermodynamics and heat transport physics. Heat sinks are defined by measured heat capacity, thermal conductivity, and energy redistribution efficiency, not by absolute temperature, a definition validated experimentally across solids, fluids, and planetary materials. Real-world implications, even very large heat inputs to the crust represent only a small temperature increase when redistributed into the mantle. In engineering and planetary physics, heat sinks such as oceans, metal heat spreaders and planetary interiors routinely absorb large heat inputs from hotter or cooler sources alike, provided a temperature gradient and transport pathway exists without requiring the sink to be insatiably cooler than the heat source. 2. Mantle thermal diffusivity is low, but bulk heat storage is high, allowing absorption without rapid temperature rise. What scientists mean, low diffusivity slows conductive heat loss, while high heat capacity allows energy to be absorbed internally without extreme temperature spikes. How we know, laboratory measurements of mantle mineral thermal properties and global heat flow constraints, real world implications. The mantle can absorb large quantities of heat quickly by a mass exchange and convection without immediate radiative loss. Number 3, mantle convection continuously redistributes absorbed heat away from the crust mantle boundary. What scientists mean, convective transport heat by moving material, preventing localized heat buildup. How we know, numerical convection models and seismic imaging show large scale circulation throughout the mantle. Real-world evidence, upwelling and downwelling structures imaged by topography indicate continuous internal heat redistribution. Heat transport into the mantle does not require heat to flow or follow temperature gradients along its path because advection carries thermal energy as internal energy within moving material. When crustal rock is heated and mechanically weakened, pressure gradients, gravity acting on density, contrast, and basal shear from the mantle flow can drive downward advection across the mantle boundary, transferring the heat into the mantle regardless of the temperature structures along the transport route. Once within the mantle, the absorbed heat is redistributed by mantle convection, which is governed by buoyancy and density gradients largely linked to temperature dependent viscosity rather than by conduction alone. The mantle therefore functions as an effective heat sink not because it is uniformly cooler, but because its immense heat capacity and active convective circulation rapidly dilute and disperse incoming heat, preventing localized thermal accumulation while delaying final radiative loss to the surface. In other words, the mantle has a very high specific heat capacity, and advection is not required to move along a thermal gradient because advection is mass flow, not direct heat flow. And so the heat is being carried within the material itself. So, and mass flow is much faster than conventional heat flow. And so, if you've got advection occurring in the crust, then you've got heated material that's moving really fast and transporting this heated material into the upper mantle. Okay, advection does not require heat to move down a temperature gradient. I already mentioned that because it is not a diffusive process. That's what conduction is. Like conduction, it is transports heat by carrying the internal energy of moving material. When crustal rocks are heated and mechanically weakened, pressure gradients, gravity acting on density contrast, and basal shear from fast mantle convection can drive downward mass motion across the moho. I already mentioned what the moho was. The heated crust advacts into the upper mantle because force balance demands mass redistribution, not because heat is flowing toward a colder region. The heat simply goes where the rock goes. Temperature gradients becomes relevant only after the heat has entered the mantle, where convection redistributes it internally. Okay, here's some sources also. The mantle as a heat sink. I got the sources at the bottom. You can see I got a couple peer-reviewed sources here. They also talks about this and equations that are used in those sources. Um, uh, Let me read the second one. Peer-reviewed geothermal research confirms that Earth's subsurface temperature redistribution is controlled by geothermal heat flow from deep Earth, demonstrating that the mantle serves as the planet's primary thermal reservoir and heat sink. The larger the mass, the greater its ability to absorb heat without large temperature increases. The equation given for this is delta T equals Q over M times C, whereas delta T equals temperature change, Q equals heated added, M equals mass times C, which equals specific heat. Talking about the specific heat capacity. As mass increases, temperature change decreases. Mantle mass is 4 times 10 to the 24th power kilograms. The sediment layer mass is orders of magnitude smaller. Therefore, heat sink capacity is vastly larger. The same attenuation principle becomes massively stronger. This also demonstrates that as heat propagates downward, it is absorbed by progressively larger mass, causing temperature fluctuations to weaken, which is exactly how massive thermal reservoirs like the mantle absorb and buffer enormous quantities of heat. In other words, the deeper heat goes, the more mass absorbs it, weakening temperature change. The mantle, being most of Earth's mass, is therefore the planet's dominant heat sink. Okay, let's start doing some math here. Just to kind of clarify here, I go through each step. I go through it step by step through the math, but in the slide presentation. But to prevent myself from becoming repetitive, redundant, and meticulous. I don't want to sit there and have to cover every single number, every single equation. Y'all can see it on the screen. This is mostly done for the critics because the critics will pounce on me if I don't go through every last bit of the math. And so I'm doing this mostly for the critic. You don't have to really memorize any of this stuff when you're presenting it, unless you want to memorize the conclusion that I came up with and the results and that sort of thing. That's fine. But for the most part, you can just simply present my model and refer them back to my videos if they want to see the math being defended on this. Um, as far as the critics go, if y'all want to check me out on the math or whatever, y'all can always pause the screen, go back to it, or write it down or whatnot. But I don't want to have to sit there and say each and every number there, especially when y'all can see the numbers. I might read some of the text and some highlighted points and summarize some of the stuff there, but I'm not going to go through every single number because it can get meticulous fast and there's a lot of math to go through. So let's start the math portion of this video. I do want to point out that my model is not math dependent. That just means the validity of the model doesn't depend on the math, but the math does show it is important to the model in the sense, and it is part of the model in the sense that it does actually show that my model actually does work. So without further ado, let's dive in. Heat sources. Okay. We're going to start with heat sources. Accelerated nuclear decay, equivalent deep time interval represented by accelerated decay, 500 million years. Just to clarify, I use the numbers that are and the data that was made by the rate team research on accelerated decay. So I'm using their values and their equations and their numbers on this. And she'll talk about seconds per year, radiogenic heat power represented by the isotope system, including uranium, thorium, potassium, plus added isotope systems such as rubidium, strontium, and as a rate examined set. P radio equals 3.80257 to 13 power watts. So much power that's involved. That's what the P stands for, power. This method assumes accelerated decay releases during the flood year the same total radiogenic energy that would normally be released over T equivalent equals 500 million years across the included isotope systems that 6.0 over 29 power or per 29 power joules um, radiogenic power of about 38 terawatts over the chosen equivalent interval. It gives you some numbers there. So if you later decide the appropriate P radio should be 20 terawatts, a commonly cited present day ballpark for total Earth radiogenic heat, depending on model, the exact same steps would yield about 3.16 to the 29th power joules instead. The steps don't change, only the assumed P radio or the isotope inventory behind it changes. Okay, step one, convert years to seconds. Okay, those are the numbers. Conclusion of step one, equivalent second or T equivalent second equals 1.57788 times 10 raised 16 per second or seconds. Step two, energy equivalent power time. Got the numbers there. Now multiply the metasis. If y'all guys want to know the definition, I'll give you a definition. I don't have it in front of me. I actually looked it up to see what that is. It is actually a mathematical term, but I'll have to look that up to let you know what that is if you guys want to know what it is. 3.80257 times 1.57788 equals 5.99999, yeah, approximate 6.0. So E, and then you got those numbers. Conclusion of step two, final answer. E and is approximate 6.0 times 10 raised 29 joules. That's how much accelerated nuclear K is as far as generated during the flood year. Runaway subduction. Okay, for this I just used Baumgartner's number, which is 10 to the 28th power. A second global heat source arises from catastrophic plate tectonics. Dr. John Baumgartner's numerical modeling of mantle convection and runaway subduction provides the most sophisticated framework for flood geology to date. His calculations show that when plate velocities are accelerated by approximately 10 to the 9th power times, that's a billion times present rates, the thermal release from friction, slab pull, and associated processes amounts to around 1.0 times 10 to the 28th power joules. That's the same as saying 10 to the 28th power joules. This value was set by Baumgartner as it emerges directly from the physics of Baumgartner's model. Because of this, most young Earth researchers adopt this figure as the standard estimate of CPT's thermal contribution. And into step one, this is fountains of the Great Deep. Step one, heat liquid water from, and it's giving the fountains of the Great Deep how much heat is generated from that. There's the numbers there. Conclusion to step one, 3.10 or 3.10365 times 10 raised 26 joules. Vaporize the water at 100 degrees Celsius, latent heat. And it gives the numbers there. Conclusion is step 2, 2.2374 times 10 raised 27 joules. Okay, step 3, superheat steam from TB to TL, sensible heating of steam. And gives the numbers there. Conclusion is step 3, 6.93 times 10 raised 26 joules. Step 4, total fountains of Great Deep thermal energy. And the final conclusion is 3.24 times 10 raised 27 joules. Fountains of the Great Deep, this estimate scales linearly with release water mass M and with assumed steam temperature TF. So plausible choices naturally yield a range 10 to 27 power to 10 to 28 power joules. About as much heat as the runaway subduction would generate. Volcanic heat, and I got step 1. You see the numbers. So sensible over m cube equals 3.948 times 10 raised 9 joules per meter cube. Conclusion to step 1, sensibility over m cube equals 3.948 times 10 raised 9 joules per meter cube. Step 2, latent heat release of unit volume. Got the numbers there. Conclusion, step 2. 1.12 times 10 raised 9 joules per meter cube. Step 3, total heat release per unit volume. This is volcanic heat. Conclusion to step 3, 5.068 times 10 raised 9 joules meters cube. Step 4 to volcanic heat. Conclusion step 4, 5.068 times 10 raised 18 joules per kilometers cube. Okay, meter impacts, core physics, kinetic energy of one impact gives the equation. Mass of spherical impactor, m equals 4 over 3 times pi times r cube times p, or times rho, excuse me, times rho. Rho in Greek looks like a lowercase p, just so you know. So that's actually a rho. Meteor impacts, we model flood year impacts as the equivalent of in medium to large oceanic impactors. Numbers of impactors, n equals 10. Impactor diameter, d equals 10 kilometers. R equals d over 2 equals 5 kilometers equals 5.0 times 10 raised 3 meters. Impactor density, stone asteroid, P equals 3,000 kilograms over M raised 3, or M cube. Impact velocity, conservative for Earth crossing objects. Well, anyway, the numbers are given there. Conservative for total energy deposited, accounts shock plus melting plus heat dominant. Step 1, volume of one impactor gives that. Conclusion to step 1, 5.236 times 10 to the 11th power meters cube. Whoops. Step 2, mass of one impactor, m equals v times rho, m equals 5.236 times 10 to the 11th power times 3,000 kilograms. M equals 1.5708 times 10 to the 15th power kilograms. Conclusion to step 2, meters equals 1.571 times 10 to the 15th power kilograms. Energy of one impactor gives the numbers there. Conclusion to step 3, 3.14 times 10 to the 23rd power joules. Step 4, total energy for n impactors. E total equals n times E1 times L for heat. And it gives the numbers there. Conclusion is step 4, 4 at 10. For 10 impacts, as the total conclusion is 3.14 times 10 raised 24 power joules, or raised 24 joules. Um, Important scaling to the flood year total used 4.0 times 10 to the 26 power joules. The 4.0 times 10 to the 26 power joules figure corresponds to a larger total bombardment that just 10 impacts of this size. A clean way to express the flood year total is E total target equals 4.0 times 10 to 26 power joules. So the required number of 10 kilometer impacts with the same V and rho would be, and then it gives the numbers there. Final conclusion, flood year impact heat used, E impacts approximate 4.0 times 10 to the 26 power joules. Impact heating can reach very large totals, either by many mid-size impacts or fewer, larger, faster impacts, because E scales as E is proportionate to R cube times V square. Doubling velocity increases energy by 4 times because v to square. Doubling diameter increases energy by 8 times because of r cubed. The number 4.0 times 10 raised 26 joules is not uniquely determined without specifying a bombardment scenario. Count sizes, velocities. The math above is the correct physics framework. The scenario assumptions determine the total. Step 1, put everything in 10 raised 29 units. Okay, here's the heat that's been generated. Exonuclear K, 6.0 times 10 raised 29. CPT, or runaway subduction, equals 1.0 times 10 raised 28, which equals 0.10 times 10 raised 29. Um, Fountains of the Great Deep, 3.24 times 10 raised 27 power equals 0.034 times 10 raised 29. Impacts equals 4.0 times 10 raised 26 power. Volcanic heat, 4.7 times 10 raised 24. Step 2, sum the coefficients, the totals, and it gives the numbers there. Final conclusion, this is how much heat total that is generating during the flood year is 6.136 times 10 raised 29. Of course, with accelerating nuclear decay is obviously the vast majority of the heat during the flood year. Okay, it gives the table here. It's basically the same thing, just gives you the numbers in a little bit more neater, organized way, so you can kind of see the numbers if you want to copy the table or something. Table 1, all heat sources are calculated from known estimates from the literature using the AI tool ChatGPT. These represent the best conservative estimates and are far more accurate than the ones the critics had devised. Okay, now we're going to talk about the speed of convection. Step 1, start with total flood heat given. That's the total we just went over. Step 2, apply my expelled to surface atmospheric by volcanism fraction given 0.0163. And it gives the numbers there. Step 3, compute heat retained, absorbed, or absorbed by the mantle given method, and gives the how much was absorbed by the mantle. Step 4, convert mantle heat to an average mantle temperature rise using mantle heat capacity given inputs. Gives the numbers there. It also gives the delta T average and that sort of thing. Step 5, optional branch used before. Convert average to an upper mantle peak anomaly given upper equals 0.30 delta T. Upper equals delta T average. Alpha upper or over alpha upper equals 150.89958 over 0.30 equals 5.02996 times 10 raised 2 or 10 square Kelvin equals 502.9986 Kelvin. Step 6, set mantle thickness given. D equals D mantle equals 2.9 times 10 raised 6 meters. Step 6, choose physical parameters used in the prior run given, and it gives the rho equals 4,500 kilograms over m cube, and then gives the numbers there. You can kind of copy them if you need to. Step 8, compute Rayleigh number from the heat derived delta T. This is where heat leads to convection intensity enters Rayleigh equals P times G times A or alpha times delta T times D cube over kappa times eta. This right here, this equation, I have personally seen this equation used multiple times in the literature in secular sources. So this is an actual equation that is used for calculating the Rayleigh number. Okay, and scaling the amount of heat, how fast convection is flowing based on how much heat is being generated. All right, step 9, plug in the average case. Delta T equals delta T average. D cube equals 2.9 times 10 raised 6 cube Rayleigh average. It says 4,500 times 9.81 times 3.0 times 10 raised per or to fifth power times 150.89958 times 2.9 times 10 raised 6 cube over 1.0 times 10 per to the sixth power times 1.0 times 10 raised 15. And then it gives the Rayleigh average as 4.873991871464697 times 10 raised 12. Okay, step 10, plug in the upper peak case, delta T equals delta T upper, and then gives those numbers. Step 11, convert Rayleigh number to null set number before the scaling that was used. Null set equals Rayleigh over Rayleigh critical, raised to the third. Step 12, compute null set for each case. There's the numbers given there. Step 13, convert buoyancy from delta T into convection speed using the velocity scaling that was used in that prior calculation. U peak equals rho times G times alpha times delta T times D to the squared over eta. Step 14, compute speed for each case. Let's get the numbers there. Um, with the upper peak being 5.60228950760031 meters per second. Step 15, convert meters per second to kilometers per year, so it's interpretable in geology speed units. Seconds per year, 3.15576 times 10 raised 7 per 7 seconds per year, and then it gives the numbers there. Step 16, optional comparison used before, express times faster than modern using the modern speed that was used. U modern equals 0.05 meters per year. U modern meters per second equals 0.05 over 3.15576 times 10 raised 7 equals 1.584404390701 4477 times 10 per 9 power meters square or seconds meters per second. And then it gives the numbers there on the factors. And the biggest sensitivity knob in the speed step are eta, viscosity, and delta T, which came from the E total via the mantle heat capacity. If either of these change, U changes directly. U proportionate to delta T over eta, and Rayleigh changes directly, Rayleigh proportionate to delta T over eta. Okay, mantle convection speed during the global flood. This is the convection speed of 3,535,896,227 times faster over in other words, over 3.5 billion times faster than modern rates. Now, understand something. This is at the peak of the flood. It's not actually doing this speed the entire time the flood is going on. It's only doing this speed uh, uh, by the time the fountains of the Great Deep are closed. That's because the model predicts that it would escalate at that point, and then it will go down from that point. So it's basically like a well, like like a like a uphill, downhill type slope. You know, go all the way up to the very top, and that top is the 3.5 billion tons faster than modern rates. Now it is going really fast before that and after, but it's that's the fastest it's going during the flood. Is when the fountains of the Great Deep were closed at day 150. Now, this one tracks mantle speed during the flood, and it tracks it on the first month just to kind of show you how fast it's going. You can write the numbers down. You can see this. Actually, this one tracks it all the way throughout the flood. You got day 30, day 75, day 150, day 200, day 255, or excuse me, day 250, day 300, day 365. So, and you see these speeds extremely fast. Even at day 30, the first month, by the end of the first month, it's going 707,107 or 707,179,245. That's pretty fast, and that's on that by the end of the first month. Now, by the end of the flood, obviously it would have died down significantly, but even by the end of the flood, you're looking at 33,742 or 33 million and 742,238. So it's going really fast, even by the end of the flood. Of course, it will die down significantly by the post-flood period and that sort of thing over time. So it does actually work its way back down, but it's pretty fast. Obviously, day 150 will be its peak. That's where you actually see it at the highest. So you kind of can see this where it kind of goes up to that and then goes down at that point. Here's the table. It's got the same numbers. Here's another table. This table is actually showing each specific day of the flood, going all the way from like the very beginning all the way there. This is the first 15 days. Y'all can see it for yourselves. And then you got the next 30 day, or the rest of the 15 days. I think this is the maybe the first month of the flood. I got, yeah, first month of the flood. So this is day 30. So this is tracking it all the way each and every single day. So you can see how fast it's going. Convection is going very, very fast. Fast enough to trigger high-speed advection in the crust, even very, very early on in the flood, and way before it would even have a chance to melt the crust. Here's another table. This one shows the distance and speed, meters per second that the heat flow is traveling, time per hour, time per days, and you see 10 kilometers, 0.037, 75.1, and 3.13 there. Then you got 50 kilometers, 0.037, and it just kind of tracks it that way too. Mantle convection during the global flood, distance U times time, and then it gets numbers there. Distance, hour, conclusion on day one. At day one heat level, the model implies hot material and heat can be transported about 3.2 kilometers in one day along the active and weak pathways where advection applies. Mantle convection during the global flood, potential criticism, minutes to hours, the crust melts. False, show me the metric heat rating and compute the time required to reach solidus using PC and latent heat. Then compare them to transport timescale. I do deal with some possible critics' objections, but my next video, critical defense, is going to be the main one that's going to be dealing with a lot of these criticisms, including one particular criticism that I promised that I would deal with in that video. Volumetric heat rate applies on day. You got the numbers there. Like I said, this is a lot of math. It gets very meticulous quick. Step 3, average power during day 1. Step 4, convert to mental volumetric heat rate. Okay, conclusion, mental average implied mental day 1, approximate 52.4 watts per meter cube. Implied crust average accelerated nuclear K rate on day 1, and it gives the total the heat there, and during 1 year, approximate triangular ramp, peaked about 2 times the yearly average. Standard for ramp up then down. Day 1 is 1 over 150 of the peak. Linear ramp to day 150 peak. Crustal volume for averaging the crust. And it's got step 1, step 2, approximate peak power. Step 3, day 1 power, 1 over 150 peak. Day 4, like I said, this gets very meticulous quick. That's why I'm not going to be reading off every single thing or every single number. Conclusion, crust average implied on day 1. Crust day 1 is approximately 25.35 watts per meter cube. Time to reach 700 and 8 to 800 degrees Celsius from day 1. Heating rate. This is something that I really am proud of. That I tracked the time it would take to heat the rock, to melt it using the temperature. Now, the only way to properly do that is to assume the rate in which it's heating up. I know it gets hotter as time goes on, but it also gets faster, so it's proportionate to the amount of heat that's being introduced. But the only way to do that math-wise and make it simple is by assuming the rate in which it's heating up at that particular moment is the rate at which it's always heating up, even though we know it will heat up more, and it will, but it also gets faster. And I actually do anticipate this and calculate some of the other days as well. But I wanted to see how, if even day 1, if it would be fast enough. And sure enough, it is. Got the numbers there. Time energy per volume. Conclusion at day 1, implied crust average heating rate reaching 700 to 800 degrees Celsius. That's the melting temperature of rock. Takes 1.9 to 2.21 years. So even at the current heat at day 1, it would not be hot enough to melt the crust because it's that fast. at day, 3, compare that to day 1, transport in the same day. Day 1, convection, advection speed, my table, and U day 1 equals 0.037 meters per seconds. Distance moved per hour, it gives that. Distance moved per day gives that. If day 1 speed held constant, conservative my speed increases after day 1. And so I acknowledge the fact that the heat will actually go up, but that the heat that goes up will also increase the speed at which convection is going. So it will still work out either way, and speed of advection. Distance during T700, distance 700 equals U day 1 times T700, and all the gave you the numbers there. You can see the numbers for yourselves. Conclusion, even holding day 1 transport speed constant, which understates my model, the transport distance available before 700 to 800 degrees Celsius, melting temperature of rock, is on the order of 2,000 to 2,500 kilometers. And of course, this is very conservative. It understates my model. My model is actually even better than this and stronger. But this shows that it does work. It's fast enough to remove the heat before the rock is melted, even on day 1. Mantle convection advection speeds during the global flood. At day 1, the implied heating rate does not drive rock to 700 to 800 degrees Celsius in hours. It takes years, while even day 1 transport can move material kilometers per day, and transport speed increases sharply after day 1. Okay, and then I decided to do one for days 5, and I think I did one for day 15. So you can see the numbers here, distance before reaching 800 degrees Celsius, and it gives that those numbers. And here's another table on the distance speed and the movement of this heat. Day 5, and of course you got day 15, implied volumetric heating rate, day 15, time to reach 700 to 800 degrees Celsius. Ignoring latent heat conservative, it's a conservative numbers that I've got. So you got the numbers here, 51.90 days. So it would still take a while to even reach the point of melting it, even at that temperature. So that means at day 15 it would not have been hot enough. It would not be able to hot enough to melt it, because it's moving it so fast. And so the point of all this is to show you that the advection and convection are moving fast enough to be able to move the heat quick enough from the crust. It's actually moving fast enough to do that. That's the whole point of this. That's why I tracked this. So this is one thing I'm like really, really proud of, that I tracked the amount of heat, compared it to how much it would take at that rate to heat up the rock, and it would actually take longer to heat it up at that rate, which basically means that at day 15, day 5, day 1, all the way throughout the flood year, it would not be hot enough to melt the crust, or melt the crust fast enough before it's actually removed, before it has a chance to do that. Okay, mantle convection advection speed during global flood. Transport comparison, day 15, speed for my table, U equals 0.560 meters per second. Distance per day equals 0.560 times 86400 equals 48,384 meters per day equals 48.384 kilometers per day. Distance before reaching 700 degrees Celsius, holding U constant conservative 700 equals 0.560 times 3.905253 to the 6th power equals 2.1869417 to the 6th power. Meters equals 2186.94 kilometers. Distance before reaching 800 degrees Celsius gives that distance as 800 times 0.560 times 4.483809 to the 6th power equals 2.5109330 to the 6th power meters equals 2510.93 kilometers. Then it gives a table here for day 15. Then I do one for day 30 of the end of the month. Time to reach 700 degrees to 800 degrees Celsius. Again, the average melting point of rock, it says 25.95 days. Day 30 speed from my table, U equals 1.120 meters per second. Distance per day equals 1.120 times 86400 equals 96,768 meters per day equals 97.68 kilometers per day. Distance before reaching 700 degrees Celsius, holding U constant, conservative. Remember, the temperature is going to be the same in that respect because of the fact is that one way to really do the math. But it does show that it does work either way. Um, and you've got the numbers there, distance before reaching 800 degrees Celsius, and it gives you the conclusion there. And then it gives you the table there. All right, notice how the distance available before reaching 700 to 800 degrees Celsius stays around 2,200 to 2,500 kilometers across days 5, 15, and 30. In this setup, that's because in my month 1 illustration of my model, both heating rate and transport speed scale upward together, each roughly proportionate to delta T, so transport capacity rises as production rises. I also have some critical objections to claim on the zircon crystal melting. A significant objection to accelerated decay models appear to zircon fission track preservation and grain scale heat transfer. Zircons are commonly contain uranium concentrations on the order of 1,000 to 5,000 ppm, far higher than the bulk granite in which they reside. If hundreds of millions to billions of years of radiogenic decay were compressed into a short time frame, the resulting internal solid state production before, or excuse me, internal power, all right, resulting internal solid state conduction. I was right. Before reaching any larger scale cooling pathway, critics argue that this diffusion is too slow to preserve rapid temperature rise, resulting internal solid state conduction before reaching any large scale cooling pathway. Critics argue that this diffusion is too slow to prevent rapid temperature rise and overlapping thermal fields from millions of nearby zircons. Under such conditions, they contend that temperatures should or would exceed known annulling thresholds for zircon and apatite fusion tracks, roughly 270 to 350 degrees Celsius and above, depending on duration, erasing the radiogenic evidence we currently observe. From this perspective, unless heat can be removed from the crust on a very short time scale and with extremely high throughput, accelerated decay would predict widespread thermal resetting that is not seen in the geologic record. That's the argument. The response: the zircon-based objection assumes that high uranium concentration within individual crystals necessarily leads to rapid independent thermal runaway sufficient to erase fission tracks within minutes or hours. However, zircon grains are microscopic, typically tens to hundreds of microns in radius, using alpha equals 1 times 10 to the 6 power, or per 6 to the 6 power meters uh, squared per second, and a zircon radius of 1 times 10 per to the 4th power meters. Equilibration occurs in roughly 0.01 seconds. This means zircons cannot thermally isolate themselves from the host granite. Their temperature rapidly tracks the bulk rock temperature. Once this rapid equilibration is recognized, the governing question is no longer grain size over heating, but bulk volumetric heat balance, specifically whether total heat production exceeds total heat removal at the rock scale. Fission tracks annulling is time temperature dependent and does not occur instantaneously at a fixed threshold. Therefore, unless the bulk host rock reaches and sustains annulling temperatures for sufficient duration, track erasures cannot does not follow. The decisive variable is system-wide throughput of heat, not micron scale crystal self-heating. In other words, the speed, real speed, is going to be found in the bulk transport of heat. Another one is an actual critic's objection, conclusion, conduction at the micro level. A central component of the objection concerns the limits of conductive heat transport in granite at the grain to rock scale. The argument holds that even if individual zircons thermally equilibrate quickly with their immediate surroundings, the host proportional to the square root of time, because zircons are abundant, the host granite itself has relatively low thermal conductivity and diffusivity, meaning heat spreads outwardly only gradually according to diffusion scaling, distance proportionate to the square root of time. Because zircons are abundant, tens of millions per cubic meter, and often spaced only millimeters apart, their thermal fields would overlap rapidly, turning the problem into bulk voltmetric heating rather than isolated grain heating. In this view, conduction through granite cannot export heat fast enough to prevent temperatures from rising toward annealing or melting thresholds unless an extremely dense and highly efficient network of circulating fluids removes heat at short timescales. Without such large-scale, high-throughput cooling, critics argue that compressed radiogenic heat would accumulate faster than it can be conducted away, leading to widespread thermal resetting of fission tracks and other temperature-sensitive mineral systems. The conduction-based objection correctly notes that granite has finite thermal diffusivity and that heat spreads outward according to square root of time scaling. However, diffusion scaling does not imply the thermal isolation, rather it quantifies transport rates, with alpha equals or approximate 1 times 10 per to the 6 power meters squared per second. Heat spreads 1 centimeters in 2 minutes and 15 centimeters in 6 hours, orders of magnitude larger than zircon grain sizes. Because zircon's spacing before may be millimeter scale, overlapping simply means the correct analysis is bulk energy balance. The critical comparison is volumetric heat production, watts per meter cube, versus total removal capacity through conduction, fluid advection, phase change, and boundary fluxes. Conduction alone is not the sole removal mechanism in a dynamically fractured, water-rich, high-strain crustal regime. If effective heat transport coefficients are increased by permeability, evolution, and surface coupling, then heat export can exceed production even when diffusion alone should be insufficient. Thus, the argument does not hinge on whether conduction is slow, but whether total system throughout exceeds generation rate at under the assumed boundary conditions. Okay, let's talk about advection speeds next. Assume total heat. This is again from my table. It's got the heat source, total heat, the peak at day 150. Permian, which is in the Permian layer, by the way, values already used, and it gives the numbers as I already specified. Here's the table again. Okay, remember why I told you that it reaches a peak? Here's some images right here. Uh, it's 3.5 times faster, a billion times faster than modern rates at the day 150. So you can see that elevating. That's a little less than 5 months. And then the rest of the time to the end of the flood year is a little over 7 months. And that's going to be in phase two. So the first one's phase one on the first side, and the second side is phase two. There's 3 phases in my model, third phase being post-flood. And you can see right at the very end of phase one and at the very beginning of phase two, we see at day 350 at the peak. That is literally the fastest convection advection will be traveling at. And you can see this a little bit better. Here's flood year mantle convection speeds relative to modern rates. Flood year convection speeds, again, relative to modern rates. It shows a little bit more on the flood days. Got that. Got a little key there on the side. Yeah, so it's just kind of deduct different portrayals of the same thing, different graphs of the same thing. Okay, now it's time to talk about the math concerning the heat absorbed by the mantle. Because in my model, the mantle acts as a heat sink. That was a revision that I made in video number 4. And essentially, it uses the mantle as a heat sink, so it does absorb the heat. Most of the heat is absorbed. My model would work even if this was not the case, but logically it does actually follow from what I found out about the mantle. The mantle is a very powerful thermal reservoir. It can actually absorb heat very well. It's got a very high total heat capacity that's really makes it a very powerful heat sink, the most powerful in the world, and it can absorb heat very well. So um, uh, without raising the temperature very much. So it also logically follows since I'm advecting this heat into the mantle that most of the heat, not just from the mantle but the heat also from this heat generated during the mantle as well. The accelerated nuclear decay that's going off in the mantle and the crust, as well as the heat generated in the crust and the runaway subduction. The heat generated in the crust as a result of the meteor impacts, the fountains of the Great Deep, those kinds of things. We would expect the heat to be absorbed, or at least most of it, absorbed into the mantle, and so we wound up having that. All right, again, yeah, it goes over the the heat, all the heat it's generating, and how much heat is absorbed into the mantle, fraction of flood heat absorbed by the mantle, and the new numbers. Um, it gives the amount absorbed 6.0 times 10 raised 29 power to joules. Average mantle temperature rise, new numbers. And delta T mantle average 150.89958 Kelvin. Total flood heat gives the total flood heat. Then it says heat transport to surface by volcanism. New numbers. It gives that as 1.0 to the 28 power. So joules, not a lot. It's a fraction of the heat. Mantle absorbed heat for evaporates. Mantle E total. Um, uh, and so it's got the E mantle equals 6.136 to the 29th power joules, minus 1.0 to 28th power joules. That means you take away the amount of heat that's going to the surface. That tells you how much is absorbed by the mantle, which is 6.036 to the 29th power. So most of the heat's being absorbed by the mantle. Then gives the total flood heat again, gives each step, define volcanic venting term, upward heat transport, assumed heat transport upward to the surface atmosphere via volcanism. By the way, in case you're wondering how much heat I know when it goes to the surface, it's just the fact that I actually looked up how much heat in the flood layers that was determined was transported by volcanism, and they don't know for sure, but their best guess is 10 to the 28 power, or is that right? 10 to 28 power joules, and so that's how much heat I think went to the surface, and so that's how I justify those numbers. Meaning this is a portion of the heat that does not remain stored at depth, but is removed upward into the surface slash ocean slash atmosphere systems where it can be removed by surface coupling, cooling processes, evaporation, heat removal, etc. Step 2, compute the fraction of total heat vented by volcanism. Uh, Gives numbers there, meaning in this partition, about 1.6% of the flood heat is assumed to be transported upward by volcanism during the flood year. This is because 10 to 28 power joules is the best guess of heat dispelled volcanically within the flood layers made by volcanologists. Step 3, compute the fraction absorbed by the mantle. And I did that 0.9837, meaning about 98.37% of the total flood heat remains within the mantle system stored as internal energy rather than being immediately vented upward. This is calculated by minusing the amount that did not expel, like you see on the previous page, to the surface during the global flood. Step 4, computing mantle absorbed heat energy. Gives the numbers there, equivalent form, and it says mantle absorbed approximately 6.036 times 10 raised 29 joules, meaning roughly 6.04 times 10 raised 29 joules is retained, stored in the mantle as the dominant heat reservoir. All right, step 5, compute the mantle's total heat capacity. And I give the numbers there, meaning the mantle has enormous heat capacity. It takes 4.0 times 10 raised 27 joules to raise the mantle's heat average temperature by 1 Kelvin. Step 6, compute the average mantle temperature rise from absorbed heat. Um, if you don't understand heat capacity, by the way, essentially that means that it takes that much heat before 1 Kelvin of heat to increase it by 1 Kelvin of heat because it absorbs that much heat. All right. Um, compute the average mantle temperature rise from the absorbed heat. Okay, it does that, meaning if the mantle absorbs 6.04 times 10 raised 29 joules, the average global average mantle temperature increases about 151 Kelvin. Note local and upper mantle anomalies can be higher depending on how heat concentrates. Total flood heat vented upward volcanism, that'd be 10 to the 28 power. Absorbed and or stored in the mantle, that's 6.036 times 10 raised 29 joules, or 98.4% of the heat that's generated during the global flood. Resulting average mantle rise delta T is approximately 151 Kelvin. Physics notes while the mantle is a powerful heat sink or thermal reservoir. A heat sink is a physical reservoir that can absorb large amounts of energy with relatively modest temperature change because it has high heat total or total high total heat capacity, mass times specific heat. The mantle qualifies as an exceptional heat sink because it is overwhelmingly massive, 10 to raise 29 kilogram scale, and has substantial heat capacity per kilogram. When heat is added, the mantle stores it primarily as increased internal energy, raising temperature, and it can also store energy in phase changes and in redistributing thermal structure through convection. Because the mantle is so large, it behaves like a planetary thermal flywheel. It can absorb heat, huge heat pulses, without instantly forcing all that heat energy to appear at the surface. Instead, the mantle buffers the surface by spreading the heat through bulk convection and by releasing only a fraction upward through volcanic and hydrothermal pathways. In other words, the mantle acts as a deep thermal reservoir that can take in most of the injected energy quickly, while surface system experiences that energy more gradually as it is transported upward through specific transport mechanisms rather than all at once. Okay, now let's talk about the heat absorbed by the floodwaters. That's the other heat sink that I use in my model. Again, step 1, set the modern ocean mass. See the numbers there. Step 2, floodwater mass. By the way, I have the meaning also. Meaning is an approximate mass of Earth's present oceans. Step 2, floodwater mass. 2 times modern oceans due to fountains of the Great Deep. In other words, there's far more water content during the global flood. Gives the numbers there, meaning the floodwaters are modeled as having twice the mass of modern oceans. Step 3, set the specific heat capacity. It gives the heat capacity as 4.0 times 10 raised 3 joules per kilograms times Kelvin, meaning this is how much energy it takes to raise 1 kilogram of water by 1 Kelvin. Okay, step 4, compute the total heat capacity of the floodwaters. I did that, meaning the floodwaters require 1.12 times 10 raised 25 joules to warm by 1 Kelvin. This is why large water masses act as powerful heat sinks. Step 5, assume a flood water warming amount. Delta T water equals 40 Kelvin, meaning this is the modeled average warming of the flow waters due to heat input. Step 6, compute heat absorbed by flow waters, sensible heat. And it's water absorbed 4.48 times 10 raised 26 joules, meaning under a 40K warming, the flow waters can absorb 4.48 times 10 raised 26 joules as stored thermal energy. Step 6, compare the floodwater absorption to vented volcanic heat, given from earlier volcanic portion, and it gives the amount of heat. Meaning if volcanism transfers 1.0 times 10 raised 28 joules outward, then 4.48% of that can be stored simply by warming floodwaters by 40K, with the remainder available for other pathways like evaporation, latent heat export, atmospheric convection, and radiation release into space. Of course, as heat is removed throughout the flood year, this creates more room, realistically, for more heat to be absorbed by the floodwaters throughout the flood year. A significant portion of this extra water added to the Earth's current ocean mass during the flood comes from the mantle, which possesses 1 times to 3 times Earth's ocean mass. All right. The essentially, I said for the floodwaters will realistically contain more because as the latent heat is removing the heat and the water is being replenished without the heat, then the water will actually be able to absorb even more heat as time goes on throughout the course of the flood year. All right, physics note why floodwaters are a powerful heat sink. A heat sink is a reservoir that can absorb large energy inputs with relatively moderate temperature change because it has high heat capacity, mass times specific heat. Water is one of the most efficient heat sinks in nature because its specific heat is very high compared to most rocks and gases. When vast amounts of water are present, they can absorb and store enormous quantities of heat as sensible warming, and they are enable high efficiency heat energy transport mechanisms, especially convection and phase change. In a flood framework, the floodwaters function as a massive thermal buffer between the solid earth and the atmosphere, temporarily storing heat while simultaneously supporting rapid heat export through evaporation, latent heat removal, and atmospheric circulation, which can transport energy away from the surface far more efficiently than conduction through solid rock. This would also enable the floodwaters to continuously absorb heat throughout the flood year as heat is constantly released from the floodwaters and the waters are replenished by rainwater, retaining a balance. Much of this water would come from the mantle, as much of these fountains of the Great Deep. There's about 3 times the ocean mass in the mantle. In geophysical terms, the mantle water does not exist as underground oceans or steam-filled cavities, but as hydrogen incorporated into mineral crustal structures, and it gives all that. As this volatile, rich fluid migrates upward through fractions, shear zones, and magmatic conduits, pressure progressively decreases, eventually allowing phase separation into liquid water and vapor, shallower crystal levels. Okay, this just basically gives a rationale to the fountains of the Great Deep, either in the mantle or the crust. I think some hold it as the crust, some hold to the mantle. I'm open to both, but it doesn't really matter to me. But I'm just basically covering all my bases here. All right, cooling mechanisms. This talks about cooling mechanisms during the flood, latent heat removal. Step 1, define evaporation mass, meaning this is the rate at which water mass is evaporated from each square meter of surface into the atmosphere. In other words, every square meter of flood water surface is converted 0.0024 kilograms of liquid water into vapor every second, which is the mass transport mechanism that carries energy upward in the form of latent heat. Step 2, Convert the evaporation mass flux into an equivalent evaporation depth per day, and gives numbers there. Gives the meaning because 1 kilogram of water spreads over 1 meter square corresponds to 1 millimeter depth of water. 207.36 36.36 kilograms per meter square per day is equivalent to 207.36 millimeters per day of water depth over or evaporated. This provides an intuitive sense of scale. It is about 0.207 meters per day, approximately 20.7 centimeters per day, of water being transported from the surface into the atmosphere as vapor. Got step 3, define the latent heat evaporation of water. Step 4, compute the latent heat flux per unit area. And you got that, and you got the meaning there of each one. Step 5, define a surface area used in the global calculations. It does the surface area. And step 6, compute global latent heat power. Define the duration of the flood year, meaning this is the number of the seconds in 1 year. Multiplying total power by time gives total energy removed. Compute latent heat removed over a flood year, meaning over the course of the flood year, evaporation condensation would remove approximately 9.64 times 10 raised to 25 joules of energy from the floodwaters through latent heat transport. This is quite significant. Step 9, compute fraction of volcanic heat removed as latent heat, and it gives that, and approximately 0.964% of volcanic heat transport to the floodwaters would be removed during the flood year by heat transport under the evaporation rate. Step 10, compute net heat remaining in flood year. Volcanic portion only, meaning after 1 year of the latent flood heat removal, approximately 3.516 times 10 raised 26 joules of the volcanic contribution would remain stored in the flood water as sensible heat. Compute fraction of volcanic heat remaining stored. Step 12, define post-flood residual heat in the floodwaters. Physics explanation, latent heat removal is fundamental, a phase change energy transport mechanism rather than a temperature gradient conduction process. When water evaporates, it absorbs energy equal to LV per kilogram without increasing its temperature, converting sensible heat at the surface into latent internal energy stored in water vapor. Though vapor transports energy upward through buoyancy-driven convection and atmospheric circulation. Under condensation, the stored energy is released at higher altitudes, where radiative cooling as space is more efficient. Because the latent heat of transport or evaporation is larger, 2.5 times 10 raised 6 joules per kilograms. Even modest evaporation fluxes produces very large energy fluxes, watts per meter square. Unlike conductive cooling through rock, which is limited by thermal diffusivity, latent transport bypasses solid state limitations and scales directly with the evaporation rate. Thus, as surface temperature rise, energy increases, strengthening latent heat flux and acting as a powerful feedback mechanism that enhances a heat transport or export from a water-covered surface system. Okay, now let's talk about cloud covering. Yes, step 1, define the evaporation mass flux under global conditions. Step 2, convert evaporation flux into evaporation per hour. Step 3, define approximate atmospheric water column for deep cloud covering. Step 4, compute the time to reload one moist atmospheric column hours. Step 5, define the baseline planetary albedo. Step 6, define the flood cloud enhanced albedo. Um, Step 7, compute albedo change due to enhanced cloud cover. It does that, gives the numbers there, meaning the model assumes a 0.15 absolute increase in albedo due to increased cloud covering. This is the key parameter that determines how much additional solar energy is prevented from entering the Earth system. Step 8, define the solar constant and global input. The meaning solar energy is averaged over the whole spherical Earth by dividing by solar constant by 4. This gives the global average incoming solar flux that the albedo acts upon. Step 9, compute the extra reflected solar flux due to the albedo increase. Step 10, compute Earth's surface area used for global power calculation. Step 11, compute extra reflected power from increased albedo. Um, Step 12, define the flood year duration. Step 13, compute extra energy reflected during the flood year. Step 14, compute fraction of total flood year heat offset by albedo reflection, meaning compared to the entire flood year heat budget, all sources, the albedo reflection term is very small fraction. This is expected because albedo acts on solar input, hundreds of watts per meter square scale, whereas the internal flood heat budget is many orders of magnitude larger. So albedo cannot be the primary cooling mechanism for the full internal heat inventory, and it's not. Fortunately, it is not. It acts only to aid in the cooling of the planet, not as a direct temperature control of the Earth. Um, then goes increase cloud covering. Step 15, compute fraction of surface transport heat comparable to albedo reflection. And it gives that when compared only to heat I had modeled as reaching the surface system in these new numbers. The portion transported upward, the albedo term remains small, but is still a real continuous cooling contribution. It reduces baseline solar loading and thereby lowers the temperature than the surface system must sustain while exporting the internally delivered heat. Then it gives a physics explanation for cloud covering, about why that increases the albedo effect. And then I could move on to volcanic cooling. I give step 1, define the solar constant. Step 2, like I said, I go through each one of these steps so that the critics themselves can see the steps as I'm going through it, going through the math and the equations. Um, and it's step 5, define Earth's surface area used for global power calculations. Step 6, step 7, step 8, compute the total volcanic cooling energy over the flood year. 4.82 times 10 raised 23 joules. For 1 year, the assumed volcanic aerosol forcing corresponds to about 4.82 times 10 raised 23 joules of solar energy being reflected away from the absorbed. This is a cooling contribution because it reduces incoming energy load on the surface atmospheric system. It gives us step 9, step 10, step 11, compare the volcanic aerosol cooling to the expelled surface transport heat portion, meaning even when compared to the only the expelled surface transport area, volcanic aerosol's reflection remains a very small fraction in this parameterization. That's to the overall heat. Its main modeled role is not to remove the deep internal heat reservoir directly, but to reduce net solar heating of the surface system so that other export mechanisms, latent heat transport and radiation release to space, operate with a lower baseline temperature burden. Volcanic heat or volcanic cooling in this treatment is modeled as a short-wave radiation effect. Okay, and I kind of give the physics explanation of that. All right, let's talk about one of my critics' favorite thing to talk about: heat released into space. Okay, again, it goes step by step, transporting heat to the atmosphere, define total flood heat input, and it's got the total amount of heat there. Define the fraction of total heat expelled to the surface atmosphere. It does that. Step 3, compute heat expelled to the surface atmosphere, meaning this is the total amount of flood heat assumed to reach the surface atmosphere system during the flood year. In this framework, the radiative cooling calculation is applied to this expelled portion because deep mantle heat does not radiate directly to space without first being transported upward. And okay, transporting the heat to the atmosphere. Step one, define the flood year excessive radiative power, delta P, from Stephen Boltzmann's constant value is the sigma. So if you see sigma, like you see P equals sigma A, T to the fourth power, sigma equals what's called the Stephen Boltzmann's constant. A stands for area. That's the area of distance it usually calculates the Earth. T to the fourth power, that's temperature to the fourth power. It always scales to the fourth power. And then it gives the equation there. Um, uh, Numbers used, it gives the numbers used there. Results already computed. It's got the delta P 3.117273911102786 to the 17th power watts, meaning delta P is the extra infrared power radiating to space above a baseline Earth-like ongoing power. Assume the effective radiative temperature rises from TO to T hot. This turns the Stephen Boltzmann law into a global power budget. How many watts of additional heat can be dumped to space during the flood year if the planet's effective emission temperature is elevated? Step 2, compute heat radiated to space during the flood year, meaning this is the total heat joules removed by infrared radiation during the flood year from the expelled to surface atmosphere portion using the elevated net radiative power, delta P, sustained over the flood year duration. Step 3, compute fraction of expelled heat radiating during the flood year. Gives the number there. Gives these numbers the fraction radiated of E export, meaning this is the fraction of expelled heat reservoir that gets radiated away from during the flood year under assumed delta P numerically 9.830 per to the fourth power means um, only a small fraction of is radiated in that single year. So most of the expelled E expelled is radiated in that single year. So most of the expelled heat remains to be radiated post-flood within the period of 1,016 years. That's 1,016 years following the flood. So the flood year, a fraction of it's removed, and then in 1016, it scales by T to the fourth power, so it is dependent upon how much heat's going up there. Very little heat's going up in the atmosphere at this point, so the temperature is slower, and so it deposits slower. My model, by the way, does not require so much heat to be transported out into space by the end of the flood. I'm not trying to get rid of all the heat by the end of the flood. I'm only dealing with the heat over time, regulating it, distributing it in a way that's actually manageable and does not actually melt the earth. It gets it out of the problem areas fast enough, etc. It never deposits it in one place at one given time, anything like that. It really does not matter to me. And I've said this in videos before, and I've said this in comment sections. It does not matter to me if the heat transported by the end of the flood or if it transported out yesterday, or if there's still heat in the internal area of the mantle and some of that heat's still going out eventually. That could happen. The escape into space is the end game of heat. It does not mean it's the only pathway it can take while it's here. um, Graham treats it like you have to get rid of all the heat out into space or it's going to melt the earth. That's just not the case. It depends on how the heat is being handled and how the heat's being managed over time. That's the main thing. It's not being dumped into the atmosphere all at once. It's not being dumped in the waters all at once. It's not being doing all that stuff and deposited in those one locations. And it's being removed fast enough from its problem areas. And I've already demonstrated that it is. So it's not a foundational to my model. It's part of my model. It does, so it would be a straw man to argue that I don't have it part of my model. It is part of my model, but it is not the most foundational to my model because it really does not matter to me how long it takes for the heat to finally, say bye bye, and leave this planet. It doesn't really matter to me. The mantle is not an ice cube today. It's still very hot. And so that makes sense. If some decay occurred during the year, if the Earth is only 6,000 years old, we would expect it to be really hot. Um, it would take a long time. Uh, it would take a little bit at least for all that heat in the mantle to go away, and it hasn't. So we got plenty of heat there because the stellar nuclear decay current processes. The primary heat source of Earth's heat, internal heat, is accelerated nuclear decay, and it's or not accelerated nuclear decay, but nuclear decay, and nuclear decay is very very slow in moderate rates. Um, and but there's lots and lots of heat in the mantle. So I think that a lot of this heat could have been absorbed by the during the flood year, and that's fine. It works with my model. So I don't have no problem. I don't need a particular time frame for all the heat to finally leave. And of course, the 1,016 years worth of heat following that's the surface level heat. That's the heat that's already made it to the surface. But there could be still some of the heat in the Earth that could be making the surface. Uh, Release to space is the end game. It is not the only pathway in which heat can take while it's here. Transport the heat to the atmosphere. Step 4. Compute fraction of expelled heat remaining after flood year, meaning this is simple. The remainder of the expelled heat fraction not yet radiated after 1 year, a flood year, at the assumed delta P. Step 5. Compute expelled heat energy remaining after flood year. And it gives those numbers, meaning this is the absolute amount of energy or energy in joules still left in the expelled heat reservoir after one flood year of elevated infrared radiation. Step 6, compute fraction of total flood heat, E total radiated during the flood year, given total 6.136 to the 29th power joules. That's the total heat during the flood. Fraction radiated of E total, radiated flood, E total, and he gives the numbers there. Meaning this is the fraction of the entire flood year budget removed by elevated infrared radiation within the flood year. It is small because most of the flood heat in this run is assumed to be absorbed into the mantle reservoir rather than instantly available to radiate to space. So it is 1.602327566121515805 per to the fifth power, and this is the fraction of heat that is left out in space by the end of the flood year. Step 7, compute the fraction of total flood heat remaining in expelled portions after flood year, meaning it says the remaining expelled heat reservoir after 1 year corresponds to about 1.63% of the total flood year heat budget. In this run, the problem heat that is actually in the surface and atmosphere reservoir is a small fraction of the overall heat budget because most of it is placed in the mantle heat sink. Step 8, compute post-flood radiative cooling time for remaining expelled heat. It gives those numbers. This is the amount of heat that is post-flood, um, meaning this is the characteristic time required to radiate the remaining expelled heat left at the same elevated net radiative power delta P. Assume delta P remains approximate constant, same effective radiative temperature differences. Step 9, convert post-flood radiative cooling time to years. So it's basically calculating how much years is the remaining surface amount of heat going to take to radiate away. Meaning at the assumed net radiative power, delta P, the remaining expelled heat would take about 1.016 to the third power years, which is 1,016 years following the flood, to radiate away if that elevated effective radiative condition persists and if no other sinks removed additional heat. Physics explanation. This calculation is used to Stefan-Boltzmann's law. P equals sigma times A times T to the fourth power uh, to model the maximum scale inferred heat loss to space from the flood system once a fraction of total flood heat is transported into the surface atmosphere reservoir, expelled. A baseline radiative state is defined by TO 255 Kelvin with ongoing power PO equals sigma A TO4 and a flood elevated radiative state is defined by T hot 350 degrees Kelvin with outgoing power P hot equals sigma AT hot to the fourth power. The net additional radiative export capacity is therefore delta P equals B hot minus PO equals sigma A over T hot to the fourth power minus TO to the fourth power, which in this run equals 3.1172739111027866 to the 17th power watts over one flood year. T flood equals 3.154 to the seventh power seconds. The total energy radiated above baseline is E radiated flood equals delta P times T to flood equals 9.8318819115618188 to the 24th power joules. Comparing this to the expelled heat reservoir, E expelled equals 1.000168 to the 28th power joules. Shows that only a fraction radiated of E expect equals 9.830230436904 per to the fourth power of the expelled reservoir is removed by infrared during the flood year. During uh, leaving E left equals 9.9918481180 to the 27th power joules. That's how much heat was left post-flood. Relative to the entire flood heat budget, which gives the total heat budget there, the radiative fraction during the flood year is fraction radiative of E total 1.6023275612154805 per to the fifth power, while the remaining expelled reservoir corresponds to the fraction left of E total 1.6283976724387843 square. Finally, the post-flood cooling time of the remaining expelled heat at the same time. Radiative power is T post equals E left over delta P equals 3.205 16055960447 to 10th power per seconds equals 1.016270150906967 cube years. Physically, this is a global energy balance estimate. Once heat is in the surface atmospheric reservoir, the rate limiting step for final removal is the planet's net ability to radiate heat energy to space, which scales very strongly with the effective radiative temperature T to the fourth power. Okay, here's one. Does the heat burn up the atmosphere with 1,000-degree heat? The temperature used in the equation is the effective radiative temperature, not the literal temperature of the entire atmosphere or surface area. In the calculation we used, the baseline planetary emission temperature was TO equals 255 Kelvin, which corresponds to about negative 18 degrees Celsius. The standard effective emission temperature of Earth used in climate physics. For the flood year test, we assumed a high emission state of T hot equals 250 Kelvin, approximately 77 degrees Celsius. The Stefan Boltzmann's law, P equals sigma AT to the fourth power, was then used to compute the difference in outgoing infrared power between those two emission states. Delta P equals sigma A over T hot to the fourth power minus TO to the fourth power. That difference represents the additional radiative power to space, not the temperature of the atmosphere itself. The important point is that 350 Kelvin is nowhere near thousands of degrees. It corresponds to roughly 77 degrees Celsius, which is comparable to temperatures reached in modern hydrothermal systems, volcanic environments, and hot ocean waters near geothermal vents. Moreover, the effective radiative temperatures of a planet is not the same as the temperature of the entire atmospheric column. Earth today has an effective emission temperature of 255 Kelvin, even though the average surface temperature is about 288 Kelvin, 15 degrees Celsius. The emission temperature simply represents the temperature of the level in the atmosphere where most infrared radiation escapes to space, therefore increasing the effect of radiating temperatures in the model means the planet is radiating heat away from or radiating heat more effectively or efficiently, not that the entire atmosphere has become a furnace. In other words, it will not burn up. Alright, because the Stephan-Boltzmann's relation scales as T to the fourth power, even moderate increases in the effective energy temperature greatly increases the rate of heat loss, raising the effective emission temperature from 255 Kelvin to 350 Kelvin increases the outgoing radiative power enough to reduce a net excess of delta P approximately 3.12 times 10 to the 17 power watts above baseline. That additional radiation power is what allows approximately 9.83 times 10 to the 24 power joules heat to be removed during the flood year in the calculations. In the calculation, the physics therefore does not require an atmosphere at thousands of degrees. The radiative export is driven by T to the fourth power dependence of infrared emission, meaning relatively moderate increases in emission temperature produces very large increases in radiative heat loss. At these calculated temperatures, there is also no physical mechanism that would cause the atmosphere to burn up. Air is primarily composed of nitrogen N2 and oxygen O2, which are extremely stable molecules under ordinary planetary temperatures. Combustion requires both a fuel and a sufficient activation energy to break molecular bonds, but the atmosphere itself is not a fuel source. Temperatures on the order of several thousand kelvins are required before atmospheric gases begin to significantly dissolve or ionize. Conditions typically associated with re-entry plasmas or lightning channels. By contrast, the effective radiative temperature used in calculation, 350 degree 50 Kelvin, is only moderately above modern tropical temperatures and far below any threshold that would chemically destroy atmospheric gases. Even if surface environments experience localized higher temperatures near volcanic or hydrothermal systems, those conditions would remain well within the range where the atmosphere remains chemically stable and capable of transporting heat upward to space. Alright, let's talk about model predictions. My model makes a number of predictions. Let's get into those. Okay, um, let's talk about first the logic of falsification. The fallacy of confirming the consequence. If P, then Q. Just because P is true doesn't mean Q is true. That's where some people think the theory becomes true if it has a confirming prediction. That does not actually make the theory true. It could be true, um, but the object of it is that it's not false. And meaning, I know it seems like counterintuitive, but essentially you're saying it's not proven false yet, because in order to be false, it has to make a false prediction. If it makes a true prediction, then it could be true, but at least it hasn't been proven false. You see what I'm saying? This is a fallacy in logic. There could be other alternative explanations why P is true that may not be because Q is true. This type of argument is invalid. Denying the antecedent. If X, then Y, not X, therefore not Y. This is a valid argument. This has to do with falsification of a prediction or theory, falsification of a prediction or a theory simply because it makes a false prediction. If it makes a true one, that doesn't guarantee that it's true, but at least we know that it hasn't been proven false. But if it makes a false prediction, then that guarantees that it is indeed false. At least the theory, model, or a particular hypothesis, or whatever the case may be. Um, doesn't mean the model or theory are true. Even though the true predictions doesn't mean the model is of the theory is true. A prediction that makes a false claim is falsified. Additional note: I'm not saying that success predictions are not good for science. That should be science. I think it started to twist into scientist. I don't know why that says science. I guess that scientist. It's supposed to be maybe it's supposed to be scientist. For science, they are, but science doesn't progress through successful predictions, but through falsification of predictions. If my model couldn't be falsified, it's no good scientifically. In other words, it has to at least have a falsifiable criteria. It has to be have the ability to be proven false. Successful scientific predictions places my model as a successful scientific model. Okay, prediction one. My model predicts that more heat you add to it, the stronger and more force efficient it gets. This is because it's one, thermally driven, and two, positive, or has is composed of a positive feedback loop system. And these two actually make my model able to, and these are the two fundamental foundationals of my model. That's what foundationally makes up my model: the fact that it's driven by the heat, and the fact this is a positive feedback loop. Um, and so it makes sense that as more heat is added, it increases. That also includes over time when the heat is being added during the flood year. As more heat is being generated, the stronger the system becomes, and everything kind of increases proportionate to that. Prediction number two, my model predicts as the heat increases, we would predict and expect the feedback system to weaken, but the effect would cause the thermal load on the cooling mechanism and system processes to lighten, thus effectively producing the same results. This comes from the fact that this is thermally driven positive feedback loop system. Prediction number three, we predict that the system will reach its peak around day 150 when the fountains of the Great Deep had closed, causing the highest of volcanic eruptions. We had predict this would be, or I would predict it, would be found in the Permian layer. This was expected because all of the geologic activity and most of the heat sources had ceased by then, which also served as the height of the flood, and accelerating nuclear decay had greatly reduced speed by that point. This would also be the fastest convection and advection speeds in the entire global flood. We expected this due to most of the heat and geologic processes being internal, and most of these processes being tied to the fountains of the Great Deep. We would expect volcanism, the primary transference mechanism in this model, will be the most intensified at day 150 when the fountains of the Great Deep had closed. Prediction number four, my model predicts a decline of volcanic activity at the first post-flood layer, but still higher than the average. This is due to the weakening of the positive feedback loop system, but even though it is weaker, it is still in effect, and so the numbers will still be higher than normal. Prediction number five, within the post-flood layers, following the flood, the volcanic activity would be more spurious with various rises, which I call hotspots in various locations, while being lower in others in terms of intensity. This is due to the fact that the volcanic activity is more regional or more regionally defined during the end of the flood year, and some of the heat still transported in the mantle would disperse volcanically, but more randomly. Okay, so I have five predictions that I made for my model so far. My model predicts, okay, prediction number one, my model predicts that the more heat you add to it, the stronger and more efficient it gets. Everything within the system increases proportionate to the heat being added to the system as the system is feeding into itself. This comes from the fact that this system is both thermally driven and a positive feedback loop. All right. Verification. This was verified when a critic had attempted to increase the heat load by adding friction to the accelerated flow of the heat or convection speeds. When this was calculated by me, the resulting increase in heat made the system even stronger and more effective, resulting in the same or similar results as before. The boost in heat load when fed back into the positive feedback loop had increased everything proportionally to the amount of heat that was being introduced as the system was being fed back into itself. The effect was the same, verifying the early prediction made with the model. My model predicts as the heat decreases, we would predict and expect the feedback system to weaken, but the effect would cause the thermal load on the cooling mechanisms and system processes to lighten, thus effectively producing the same results. This comes from the fact that this is thermally driven positive feedback loop system. This prediction was also made early on, and it was verified when a critic had noticed in my initial video that my total from all my heat sources in the video, the depth of the heat problem, that's the name of the video, had been inflated by 3 times as great. I had already biblically commented to a Christian YC what would happen if the heat load was reduced. I had calculated everything based upon the new total of my heat sources, now 3 times less than they were, and the effect was the same results where basically the same. As the heat decreased, the system weakened. But in turn, this lightened the heat load on the cooling mechanisms and processes of the system, resulting in the same or similar results as when thermal input was heavier. Prediction number 2 was verified. And prediction number 3, we predicted the system will reach its peak around day 150. I already read this. Also, an early prediction made the model. This one proves the most interesting. Rarely do we see YCs modeling the exact flood layer by which the day 150 day had fell on, but my model predicted the intensity level of volcanic activity throughout the flood, elevating and rising to a specific peak before descending down until the end of the flood, where although volcanic activity is still happening, it is not extreme, where the system is still in effect above normal, but not extreme and more regional than global. There could be some extreme volcanic activity regionally, but not on a global scale. This intensity level in volcanic activity was able to be tracked via the amount of volcanic activity in a specific flood layer, which would track the intensity of volcanic activity on a global scale. So essentially, I looked at the amount of volcanic evidence that was available to determine how intense the volcanic activity was during that level or stage of the flood. Okay, here's a table that actually shows this prediction of the high intensity. You notice around the Permian level, that's the maximum intensity, and then you notice it actually going down from that point. So it elevates up to maximum intensity less than 5 months, 150 days at the Permian level, and then it starts decreasing after that. So my prediction of my model was fulfilled. Okay, prediction 3. This one I looked through each one of the flow layers on the prediction 3. Volcanic evidence and Cambrian rocks exist, but is generally limited to scattered island arc, volcanism, and limited basalt. I looked at each one of the levels here to determine the intensity of volcanic activity on prediction number 3. So I looked at each and every single one of this to determine that. Like I said, it has the intensity here, and it matches my models. You can see it here. Cretaceous. Okay, it goes all the way up to day 150. See this graph right here, and this is a technical chart. You see phase 1 and phase 2, and you see it go up to day 150, and it elevates to that, and then starts dropping, and it matched the what was predicted by my model. Here's another graph. I like these graphs that I made. They're pretty cool. Gives you kind of an idea of the successfulness of my model and what it predicts. It does make best sense of the evidence at hand. Okay, let's talk about prediction number 4. This has to do with the post-flood area, or looking at the post-flood layers. If you notice the chart, the Paleogene layers start us off with moderate intensity. In later tests of post-flood layers, this is identified as medium to high, meaning it starts out high and then reduces to medium, which is above low, which is what is being expected since the previous layer had an intensity level of high and it had been reducing following the flood. The Paleogene is split into three groupings, with early Paleogene being labeled as Paleocene, which is what the later tests recognize as high medium, which makes sense since this layer immediately precedes the global flood. See the table for verification of volcanic intensity with the post-flood layer, and see my breakdown of post-flood layers volcanic intensities below for further clarification and verification of this. Okay, prediction number 5, within the post-flood layers. Following the flood, volcanic activity would be more spurious and with various rises, of which I call hotspots, in various locations, while being lower in others in terms of intensity. This is due to the fact that the volcanic activity is more regional or more regionally defined. Following the end of the global flood, and some of the heat still trapped in the mantle would disperse volcanically, but more randomly. Verification. This one is a recent prediction of mine. I have predicted that due to some of the heat still being stored in the mantle, and due to the fact that the fountains of the Great Deep had closed and the global flood had ended, that the volcanic activity would be sporadic, random, and more regional than the previous volcanic activity, to the point where such activity would have geographic moments of intense eruptions, while in some geographic areas a much more lower intensity. This was verified in a recent test whereby I looked at the volcanic intensities of various post-flood layers. And prediction number 5 of the model states that after the flood, global flood peak associated with the flood, volcanic activity should decline in overall intensity and become increasingly regional rather than global, synchronized. The geologic record of the post-flood layers with the Paleocene, Neogene, and Quarantine post-flood layers shows a pattern consistent with this expectation. Instead of a single worldwide volcanic maximum, volcanic intensity appears concentrated in particular tectonic provinces at different times. For example, strong volcanic activity occurred in the North Atlantic region during the Pliocene, while western North America experienced major volcanic flare-ups during the Oligocene and the Miocene. During the same interval, significant rifting volcanism developed within the East African rift system, while subduction-related volcanism continued at modern to high levels in the Mediterranean Arc and Pacific Arc systems through the Pleistocene. These peaks do not occur simultaneously across all regions, but appear as localized spikes associated with specific tectonic environments. The resulting pattern increases the post-flood volcanism is characterized by regionally regional concentrations of activity rather than a single global phase of extreme volcanism, matching the model's prediction that volcanic intensity following the flood would become more regionally defined as the Earth's tectonic systems stabilized and localized volcanic processes dominated the geologic record. Here's a look into that. The post-flood activity, global intensity, shows that it's different for every region. Um, the regional volcanic intensity observed in the Ice Age layers further supports the prediction that the post-flood volcanism would become increasingly localized rather than globally synchronized during the post-flood Ice Age, represented primarily by the Pleistocene layer and continued into the Holocene layer. Volcanic activity is distributed unevenly across major tectonic regions. Certain areas, such as the North Atlantic volcanic provinces associated with Icelandic plume activity, show elevated levels of volcanism during the Pleistocene, while other regions, such as Western North America, display more modern or declining activity. At the same time, persistent volcanism continues within rift systems like the East African Rift and within subduction-related volcanic arcs surrounding the Mediterranean and the Pacific basins. These regions maintain ongoing volcanic activity, but do not exhibit simultaneous global peaks. Instead, the pattern reflects localized volcanic systems operating according to their specific tectonic settings. The distribution reinforces the broader trend seen in post-flood geologic layers, where volcanic intensity becomes increasingly regionally concentrated rather than globally uniform, consistent with the prediction that the tectonic and mantle processes following the flood would stabilize into discrete volcanic provinces rather than producing a single worldwide phase of extreme volcanism. Okay, you can see phase 5 again during the Ice Age. Here's another table. Notice it's very lopsided, and this is because we would expect it to be more regionally defined um, than uniformly global like it is during the flood. So prediction 5 is matched within this. Okay, let's talk about what's some critics call the freezing problem. This is the inverse heat problem, and I'll explain what that freezing problem is. A lesser known criticism of catastrophic flood models is sometimes called the freezing problem, which is essentially the inverse of the well known flood heat problem. The argument begins by noting that during the flood, the Earth would have experienced extreme atmospheric disturbances, massive rainfall, dense cloud cover, and prolonged reduction of incoming solar radiation. Critics argue that if the sunlight were significantly blocked by thick storm systems and volcanic aerosols, then the planet would lose more heat to space than it would from the sun because Earth radiates infrared energy continuously according to the Stephan-Boltzmann's relation, P equals sigma A T to the fourth power. The loss of incoming solar energy could theoretically drive rapid planetary cooling. Under such condition, the oceans and atmosphere could experience substantial temperature drops, potentially freezing large portions of the floodwaters. That is the argument of the so-called freezing problem. In this argument, criticism claims that catastrophic flood models face a thermodynamic dilemma. If tectonic and volcanic processes did not produce enough heat, then the planet would cool rapidly due to reduced solar input and increased radiative loss to space. Large-scale evaporation, storm systems, and cloud cover could further enhance cooling by increasing planet albedo, reflecting more sunlight from the Earth. This would reduce the absorbed solar flux according to the relation P solar equals 1 minus alpha over SA over 4, where S is the solar constant and alpha is planetary albedo. If albedo increases substantially during the flood, the amount of solar energy entering the climate system decreases um, potentially during a significant drop in global temperature. Critics therefore argue that the flood models must solve two opposing thermodynamic constants simultaneously. On one hand, catastrophic geologic processes could produce too much heat, creating the traditional heat problem. On the other hand, if those heat sources are insignificant or quickly dissipated, the planet could experience severe cooling due to reduced solar radiation, enhanced energy lost to space. In that case, the floodwaters themselves could approach freezing temperatures, which would create a completely different environmental crisis for marine life and the global hydrological system. For this reason, the freezing problem is sometimes presented as a mirror image of the heat problem. Critics claim that the flood models must explain how the Earth avoids both extreme overheating and extreme cooling during the same catastrophic year. In other words, the planetary energy balance must remain within a narrow thermodynamic range that prevents the oceans from either boiling or freezing despite dramatic changes in tectonics, volcanism, atmospheric composition, and solar absorption. Now, I've already talked about on how my model actually deals with the heat. So we're going to deal with this particular argument next. Now, um, The GTF model resolves both of these objections. The apparent dilemma between overheating and freezing arises only if the flood system is treated as a simple one-directional energy process. In reality, the Earth during the flood would have functioned as a coupled thermodynamic system with multiple feedback mechanisms operating simultaneously. The geothermal feedback model, or GTF model, proposes that the flood environment behaved as a thermally driven positive feedback system, meaning that increases or decreases in heat automatically strengthen or weaken the physical processes that regulate planetary temperature. In thermodynamic terms, the planetary energy balance can be expressed as dE over dt equals P in and P out. E equals total energy of the Earth system. dE over dt equals rate of change of energy with time. Pn equals power entering the system, solar plus geothermal. P out equals power leaving the system, mainly radiation to space, where Pn represents incoming energy source and P out represents energy loss from the system. During the flood year, Pn would include geothermal heat from tectonic activity and volcanism, while P out would include latent heat transport, atmospheric circulation, cloud albedo effects, and infrared radiation to space, governed by the Stefan-Boltzmann relation P equals sigma A T to the fourth power, because radiation increases with the fourth power of temperature. Even moderate increases in effective radiation temperature dramatically increases the rate at which heat is lost to space. The key feature of the GTF model is that the flood system contains self-regulating thermal feedbacks. When heat produces increases, processes such as evaporation, atmospheric convection, cloud formation, and radiation heat loss intensify, accelerating the removal of heat from the system. Conversely, if heat production decreases, those same processes weaken, reducing the rate at which heat escapes and prevents excessive cooling. In other words, the cooling mechanisms respond dynamically to the thermal state of the system rather than remaining constant. Because of this feedback behavior, the flood climate does not diverge toward catastrophic overheating or runaway freezing. Instead, the coupled interaction of geothermal heat sources, mantle heat storage, advection of heated material, latent heat removal, increased cloud covering and albedo effects, radiative heat loss, creates a dynamic thermal equilibrium. The system continuously adjusts the strength of its cooling processes in response to the amount of heat present. The result is the same mechanism critics appeal to when arguing for a freezing catastrophe, such as increased evaporation, cloud covering, and atmospheric circulation, are actually part of the very processes that stabilize the system in the GTF. Rather than production, runaway, cooling. These processes operate within a feedback network that regulates the planetary energy balance and maintain the flood environment within survival thermal limits. Answering criticisms, I'm not going to be doing that here because I'm going to do it in the next video, a critical defense. So watch that video for my responses to a lot of the criticisms on that. All right, here's my conclusion. The quantitative analysis presented here demonstrates that the heat production during the flood year can be physically accommodated within a coherent geophysical framework when the system is evaluated as a coupled dynamic energy budget rather than as an isolated conduction problem. The geothermal feedback GTF model integrates multiple interactive mechanisms, large-scale mantle convection, rapid crustal advection, latent heat removal from the floodwaters, the floodwater heat absorption, atmospheric energy redistribution, and radiative loss to space. When these processes are modeled together using established physical relations such as Rayleigh number equals P times G times alpha times delta T times D cube over kappa times eta, and the Stefan-Boltzmann's law, P equals sigma A T to the fourth power, Sigma, of course, is the Stephen-Boltzmann constant. A is area of the Earth, and T to the fourth power is temperature to the fourth power. The system behaves as a thermally self-regulating feedback loop rather than a runaway heat trap. Calculations show that the overwhelming majority of the flood-generated heat can be absorbed by the mantle, which acts as an enormous thermal reservoir due to its mass, 4 times 10 to the 24th power kilograms, and heat capacity, 4 times 10 to the 27th power joules per Kelvin. Elevated heat or elevated mantle temperatures reduce viscosity exponentially, according to the rheological relation epsilon or E dot, excuse me, E dot equals A times sigma uh, to the eta times expected, um, dramatically increasing convective velocities and allowing heat to be redistributed rapidly through mantle and overturn and crustal advection. This temperature-dependent convection, advection, and rheology that's happening within the crust, I'll explain rheology a little bit more in the next video, along with globalized volcanism, forms the central positive feedback mechanism of the GTF model as heat production increases, viscosity drops, and convective transport accelerates, and heat becomes progressively more efficient. Such behavior is consistent with the geologic record of massive volcanism associated with the flood strata and the evidence for accelerated nuclear decay. The geologic evidence strongly supports the presence of processes operating at this scale. Flood-related strata contains vast volcanic provinces, extensive basalt flows, and widespread ash deposits, indicating eruption rates for exceeding modern levels. These eruption fractions as both a surface expression of the feedback system and a mechanism for transporting deep heat toward the atmospheric ocean onic floodwater system, where additional cooling mechanisms operate. At the surface, the floodwaters serve as a massive thermal buffer due to water's high heat capacity, while increasing evaporation, latent heat removal, cloud formation, and volcanic aerosols enhance planetary albedo and promote additional energy loss. Uh, Ultimately, the Earth system radiates energy to space through infrared emissions governed by P equals sigma AT to the fourth power, allowing the remaining expelled heat to dissipate over post-flood timescales. When the entire coupled system is considered, the GTF model demonstrates that the so-called heat problem arises largely from treating the crust and the Earth as a static closed system dominated by conduction. In reality, the Earth behaves as a dynamic multi-reservoir heat engine in which mantle convection, crustal mobility, volcanic transport, oceanic buffering, atmospheric processes, and radiative emission all work simultaneously to redistribute it and effectively remove energy. The combined mathematical modeling and geologic evidence therefore indicate that a positive feedback loop system operated as a thermally driven system regime provides a physically plausible mechanism for managing flood year heat while remaining consistent with observed geologic and thermodynamic laws. All right. Um, Thank you for joining me on here for this big evidence video. I've been meaning to do this for a while. My model is great. It actually does work. It does work with the evidence. I do have another video. I'm fixing to make that. When both of these videos have been made and edited, I will then upload them to YouTube. And I will schedule them at the same time because it's going to be kind of like a double feature. It's going to appear at the exact same time. My hope is to get these videos out by the 1st of May, May 1st, hopefully. Hopefully, I will have both videos uploaded and ready to go by May 1st. All right, so thank you again for joining me on here. Just to kind of let the critics know, I am giving you 2 weeks total for both videos, okay, to respond. And the reason is because I'm going back to school and I'll be starting classes May 18th. So you guys have 2 weeks to respond. And after that, I will shut down the responses Gotta focus on concentrate on my schoolwork. Sorry, guys. All right, but I am going to give you 2 weeks to respond to this. That's why I'm going to put it out the 1st of May. Give y'all a full 2 weeks, 14 days. Y'all have the entire 14th day to finish up reply, and then of course I'll reply back, and then that will end these reply. That will end the responses. Um, Word of advice to you critics: don't be focused too much on nitpicking every last tiny little thing you see in the slide you don't like. Um, I would not worry about trying to focus too much on the math. It's okay. We can talk about the math and the charts and the graphs. Those are all fun and interesting. But that's not going to make my model wrong if you could find a math error somewhere. Okay, so you're going to have to try to do better than that. You only have 2 weeks. I tell you guys that every single time. You always disappoint me. Don't do that. Make the most of those 2 weeks. That should give you plenty of time to watch the videos and try to come up with a response. Hopefully a halfway decent one that I can respond to, and we'll go from there. But I will not be continuing this after 2 weeks. I'm sorry, you guys, but I have to concentrate on school. My classes start May 18th. I can't wait. I want to finish off my second degree, and that way I can go ahead and start going into the graduate program at Liberty University. So that would be awesome. I can't wait. But anyway, all right, that's all for today. Thank you for watching Apologetics 101. I appreciate it, and I will see you on the next one.